Hello friends, in next few videos we will learn about how to apply Newton's law. Basically there are three Newton's law. The first Newton's law says that if you have an object that is in equilibrium, then the total forces acting on that object is zero. In other words, the net force is equals to zero. The second law relates to the force and acceleration, and it says force is equals to mass times acceleration. And finally, Newton's third law, that is related to action-reaction pair, and it says whenever you have a action-reaction pair, the magnitude of action force is equals to the magnitude of reaction force, and both these forces occurs in couple. So in this session we will learn how to apply Newton's first law, and this we will illustrate using an example. So the objective of this session is to learn to find the tension in a massless rope. So we will have a massless rope and we will try to find tension at different point of the massless rope. The problem says a gymnast with mass mg is equals to 50 kg suspends herself from the lower end of a hanging rope of negligible mass. So this is the gymnast and mass of gymnast is given. So mg is equals to 50 kg. So the mass of gymnast is given. Now this hangs using a rope. So this is the rope and this is the lower end of the rope and this is the top end of the rope. Furthermore, the question says the upper end of the rope is attached to the gymnasium ceiling. So the top end of this rope is attached to the ceiling. So this is the ceiling, that is the roof, and this holds the rope. Now the question asks, what is the gymnast weight? That is the first part. In the second part, what force in terms of magnitude and direction does the rope exert on gymnast? That is, force exerted by the rope on the gymnast. And finally, you have to calculate what is the tension at the top of the rope. So this point, that is the top of the rope. So let us do first part first and then we will do second and third part. So in the first part, we have to find weight of the gymnast. Now how will calculate weight? If you remember, we can write weight is equals to mass times gravity. Now in this problem, mass is given, that is 50 kg, and you know gravity, which is 9.8 meter per second square. So if you multiply these two, you will get 490 Newton. So this means weight of gymnast is equals to 490 Newton. So this is the first part of the problem. Now in the second part, question says what force in terms of magnitude and direction rope exerts on gymnast. So how will you do this? Now to solve such kind of problem, you have to draw free body diagram. Now how do you draw the free body diagram and how do you select the components? So if you have a system, then you try to draw the free body diagram for each component. For example, in this case, in my system, components are gymnast, rope and ceiling. So we can draw free body diagram for gymnast, and similarly we can draw free body diagram for ceiling and rope. So let us first draw free body diagram for gymnast. So we can draw free body diagram for gymnast. And we will basically denote gymnast by a point. So this is a point mass. Actually this is not a point mass. So we are making assumption or we are idealizing the situation, and this gymnast is denoted by a point mass. So the first force that is acting the weight of gymnast. So ground is trying to pull the gymnast in the downward direction, that is the weight of gymnast is acting in the downward direction. What other forces acting on the gymnast? One force is due to the rope. So if you see, this gymnast is trying to pull this rope in the downward direction. In the same way, if I apply Newton's third law, I can say this rope is also trying to pull this gymnast in the upward direction. So this is an action-reaction pair. And from Newton's third law, these two pairs will have equal magnitude. In other words, I can say force on gymnast, G for gymnast, due to rope is equals to force on rope, R for rope, due to gymnast, G for gymnast. So these two forces are equal. So I can assume these two forces are equal and the magnitude of that is F. So force on gymnast due to rope is equals to force on rope due to gymnast, and which is equals to F. So now these two pairs are basically nothing but F. So I can show this in the free body diagram. So on gymnast there is a force acting due to the rope in the upward direction, and this force is F. Now since this gymnast is in equilibrium, we can apply Newton's first law. So what Newton's first law says? This says sum of total forces is zero if the object is in equilibrium. So let us first make a sign convention, and the sign convention in this case is upward direction is positive direction. So we will apply sum of all the forces in the bidirection is equals to 0. So what are the forces that is acting in the bidirection on the gymnast? So now I know the free body diagram. On the upward direction we have force F. In the downward direction we have WZ. So I have to put a negative sign because upward is positive, then downward is negative. So this is the total force on gymnast, and this is in equilibrium. That's why this force is equals to 0. Sum of all these forces is equals to 0. This means F is equals to WZ, and we have already calculated WZ. This is nothing but 490 Newton. So now I can say force applied by the rope on the gymnast has a magnitude of 490 Newton, and this force is acting in the upward direction. So now I can say force on gymnast due to rope is equals to 490 Newton, and this force is acting in the upward direction. Now let us do the third part of the problem. So for doing the third part, that is what is the tension at the top of the rope, we have to draw the free body diagram of rope. So if you remember, so what are the forces that is acting on the rope? So let's say this is your ceiling, and this is your rope, and this is your gymnast. So gymnast is somewhere here. So on this rope, so this is trying to pull. So gymnast is trying to pull this rope. So one force that is acting on the rope is in the downward direction. That is because gymnast is trying to pull this. And the magnitude of this force will be same as in the second part. That is the F, because Newton's third law. So this force is nothing but 490 Newton that we just calculated. So this force is F. That is 490 Newton. So force applied by the gymnast on the rope is equals to force applied by the rope on the gymnast, and both are equal to F. That is equals to 490 Newton. Now the rope is massless, so there will be no weight. So no weight that is coming due to the weight or mass of the rope, because this problem says rope is massless. Now any other force that is acting? Yes, one more force that is acting in this case, because you see this rope is trying to pull this ceiling in the downward direction. So ceiling will also pull this rope in the upward direction. From Newton's third law, we can say these two forces are equal. So let us call this force as force due to ceiling, that is Fc. So this force will be in the upward direction and the magnitude is Fc. So now this is in equilibrium. So this rope is in equilibrium. We can say sum of all the forces is equals to 0. So what are the forces that is acting on this rope? So this is free body diagram of rope. So sum of all the forces. In the upward direction we have force Fc. In the downward direction we have force F. And that's why we have taken a negative sign, because this is in the downward direction, and sum of all the forces is equals to 0. This means Fc is equals to F, and we have already calculated F. This is 490 Newton. So magnitude of Fc is equals to 490 Newton. And what is the direction? So what is the tension at the top of rope? So tension magnitude is 490 Newton, and this is trying to pull in the downward direction and the ceiling is trying to pull in the upward direction. So at top point, this is a force that is acting on the thread or on the rope. Now one important point in this problem, that is, we have assumed the rope is massless. And that's why if you consider any point of the rope, so this is top point of the rope and this is bottom point of the rope. So either you calculate tension at this point or this point or this point or this point, all are same, all are equal to 490 Newton. This is only because this rope is massless. If you have mass of a rope, then you have to consider the mass of the rope in this free body diagram also. So mass of the rope will also come into the picture, and tension at the bottom of the rope and the tension at the top of the rope will not be same. And this we will illustrate in the next problem. For the time being, we can conclude here this session, and in this session we learned how to draw free body diagram and how to apply Newton's first law, that is, if an object is in equilibrium, sum of the forces is equals to 0. I hope you like this video. If you like this, then please share and subscribe and share with your friends also, and I will see you in the next video. Thank you. Hello friends. In the last video we learned how to calculate tension in a massless rope. Now in this video we will learn how to find tension in a rope that has a mass. And let us illustrate all this using a problem. So this problem says a gymnast with mass 50 kg suspend herself from the lower end of a hanging rope. So this is a hanging rope, and this gymnast hangs herself from the lower end of this hanging rope. And the mass of gymnast is given, that is 50 kg. So let us write it here. Mg is equals to 50 kg. Next, it says the upper end of the rope is attached to the gymnasium ceiling. So this is the upper end of this rope, and this is attached to the ceiling. So this is the gymnasium ceiling. We have to find the tension at the top and bottom end of the rope if the weight of the rope is 120 Newton. So the weight of rope is also given. The weight of rope is equals to 120 Newton. And what is the target variable? We have to find tension and top and bottom end. So let's call this point is point 1, that is bottom of the rope, and this is point 2, that is top of the rope. So we have to find tension at point 1, that is T1, and we have to find tension at point 2, that is T2. So this is what we have to find. Now how will you solve this problem? So to solve such problem, you have to first draw the free body diagram, and in that case you have to decide what are your component. What are the system components for which you are going to draw the free body diagram? In this case, we can draw a free body diagram for gymnast, and we can draw free body diagram for rope, and we can also draw free body diagram for ceiling, but that will not be useful in this case because that will not give any extra equation. So let us draw free body diagram for gymnast and rope, and let's try to find variable T1 and T2. Since we have two variable unknown, that is T1 and T2, if we can take two free body diagram and we can write two independent equation, we can solve this problem. So if I draw free body diagram of gymnast, so let us denote gymnast by a point. One force is acting in the downward direction is the weight of gymnast, that is WZ. Now what are other forces that is acting? Another force that is acting on this gymnast is a force that is trying to pull this up, and this force is applied by the rope. So rope is trying to lift this gymnast, or you can say hold this gymnast in the upward direction, and this force, let's call this force is T1. So we can show this force in the free body diagram, and this force is T1. So this is free body diagram of gymnast, and G denotes gymnast. Now similarly I can write free body diagram for rope. This is free body diagram of rope. Now again we can denote this rope by a point, so this denotes rope. And what are the forces that is acting on the rope? One force, this gymnast is trying to pull this rope in the downward direction. Try to see here, this gymnast is trying to pull this rope in the downward direction, and rope is trying to pull this gymnast in the upward direction. These two are action-reaction pair. Now if I apply Newton's third law, these action-reaction pair has to be equal, and this means this force is also equals to T1. What are the other forces that is acting? Now this rope has mass, so this is not a massless rope, so weight of rope will also act, and this will act again in the downward direction, and let's call this weight is WZ, that or WR, that is weight of rope. Any other force that is acting? Yes, one more force is acting in this case. This rope is trying to pull the ceiling in the downward direction. In other words, this ceiling is also trying to pull this rope in the upward direction, and the magnitude at this point is T2. That is the amount or force by which this ceiling is trying to pull this rope in the upward direction is T2. So now I can show this force here, that is T2 is in the upward direction. Now once I have this free body diagram, I can solve for unknown. So let us consider the equilibrium of gymnast and rope. Both are in equilibrium, so sum of the forces has to be 0. So first we will consider for gymnast, and let us make sign convention, that is positive direction is the upward direction. So let us first consider equilibrium of gymnast. So if I consider equilibrium of gymnast, sum of all the forces has to be 0. In the upward direction, force is acting T1. In the downward direction, force is acting WZ. And that's why we have put a negative sign. This is in the downward direction. Sum of all the forces is equals to 0. So this means T1 is equals to weight of gymnast. And weight of gymnast we have already calculated. This is nothing but 490 Newton. So tension at the bottom of this rope is equals to 490 Newton. So this is at the bottom, at bottom of rope. Now the next part, we can consider equilibrium. So this is equilibrium of rope, that is R. So if you consider equilibrium of rope, the vertical forces is T2, and what are the forces that is acting in the downward direction? Minus T1 minus WR. Now since this is in equilibrium, sum of all the forces is equals to 0. So from here I can write T2 is equals to T1 plus WR. And we have already calculated this T1 is nothing but 490 Newton. So we can plug here. So this is 490 Newton. And weight of rope is given, that is 120 Newton. So if I sum all this will come 610 Newton. So this is, now I can say tension at the bottom of rope is 610 Newton. So this is at the top of the rope. So at top of rope. So you see, in this case, the tension at top and bottom is not same. So if you see this rope, so this is the rope. At bottom you have a tension of 490 Newton. And at top you have a tension of 610 Newton. So this is top point and this is bottom point. So this tension is not same. If you remember, in case of massless rod, these two tension are same, that is T2 is equals to T1. But in this case, T1 and T2 is not equal. The upward point, that is top point, has more tension and the bottom point has less tension. And the difference is nothing but this difference is same as the weight of this rope. So you see, in a massless rope and a rope with mass, you will not have the same treatment. In case of massed rope, or in case of a rope that has a mass, you have different tension. You can basically calculate tension at this point, at this point, at this point, at this point. So if we give you the distance from top point x, then you can basically calculate tension as a function of x. That is not part of this session. Sometime else we will discuss that. The idea is, in case of a rod or in case of a rope that has a mass, tension will not be same. It will vary with the length. Finally, you can also solve this problem by taking a different kind of system, or you can say composite system. What I mean, let us try to understand. So this is the ceiling and this is the rope and this is the gymnast. Now in this case I can consider this as my system. So if I consider this as a system, what are the forces that is acting? So let's say this is my composite system and that is denoted by this point. So what are the forces that is acting in the downward direction? One is weight of gymnast. So gymnast weight will come. And then another is weight of rope. And what is the force that is at this point? This is point number 2. There is a force that is acting in the upward direction, that is T2, tension at point 2. Now if I consider equilibrium of this composite system, I can write T2 minus WR minus WZ is equals to 0. So this means T2 is equals to WR plus WZ. And this is equals to 610 kilonewton, as I calculated earlier also. Now see, if I consider this composite system, I cannot calculate T1 because I have only one free body diagram. So we cannot calculate T1. So if I consider a composite system, it's not possible to calculate T1. Basically, in this case, what is happening? T1 is becoming an internal force. So this part and this part. So the force T1 is becoming an internal force, and that's why this force does not come into the free body diagram. So if you have more forces or you want to analyze T1, then you have to break this system. You have to consider rope separately and you have to consider this gymnast separately. So this means if you want detailed analysis or if you want to solve more unknowns, you have to consider more number of components. You have to draw free body diagram of more number of components of a system. So it is always a good idea to break the system in multiple components and draw the free body diagram of each component and write down the equation and solve this equation. I hope you have liked this video, and if you like this video, please share, subscribe and discuss with your friends. Hope I will see you in the next video. Thank you. Hello friends. In the last video, we have learned how to apply Newton's first law in case of one-dimensional equilibrium. In that case, basically you write equation of motion or equation of equilibrium either along the x-axis or along the y-axis. Now in this session we will see how to apply Newton's first law when you have a two-dimensional equilibrium. We will illustrate this using an example. So this problem says a car engine with weight W hangs from a chain that is linked at ring O to two other chains, one fastened to the ceiling and other to the wall. So we have a car engine here and the weight of this engine is given, that is W. Now this engine is hung from a chain. So this is one chain. So one end of this chain is attached to the engine and other end of this chain is attached to a ring. And this ring is also supported by two other chains, this one and this one. One chain is inclined and other chain is horizontal. Now the question further says, find the expression for tension in each of the three chains in terms of W. So the tension is these three chains are different. In this chain tension value is T1, in this chain tension value is T2 and in this chain tension is T3. So we have to find T1, T2, T3 in terms of W. So in this problem what are unknown, that is what are target variable. So target variables are, so we have target variables T1, T2 and T3. So there are three target variables, three unknowns in this equation or in this problem. Furthermore, the problem says the weight of the ring and the chain are negligible compared with the weight of the engine. So we have to neglect the weight of engine, not the engine, weight of chain and the ring. So this is the assumption we have to make in this case, and that is given in the problem. That is weight of chain and ring is almost 0. So let's call this as a 0. Now how will you solve this problem? So in this case you see there are three unknowns. And unknowns are T1, T2 and T3. So if you want to solve this, you require three equations. So you require three equations. And of course these equation has to be independent. So basically you require three independent equations. Now if you remember, if you write equation for one object, you can write only two equations. If you consider a planar object, then you can write only two equations. One along the x-axis, another along the y-axis. So you have to consider more object, because if you consider one object only, you can write only two equations, but the number of unknowns are 3. So we have to consider in this case more than one object, at least two objects. So we will consider two objects and we will write equations. So let us consider two objects. And what will be these two objects? One will be engine and another will be ring. So these two objects will be engine and ring. So let us try to draw the free body diagram. So what I am saying, we have to consider one engine, one object, another object is this ring, and then we have to draw the free body diagram, and then we can write equation of equilibrium, and then we can solve. So what are the forces that is acting on this engine? One force is acting, that is weight. Another force, that this chain is trying to pull this engine in the upward direction, that is force T1. So let us write free body diagram or draw free body diagram for engine. So this point denotes engine, and this weight is acting in the downward direction. Let's say mass of this engine is m. Basically weight of the engine is given, so simply we can write w. So that is acting in the downward direction, and the tension force is acting in the upward direction, and this tension force is T1. So this is the free body diagram of engine. Now similarly we can draw free body diagram of or for ring. So let us draw a free body diagram for ring. So once again we can show ring as a point mass. So this point denotes ring, and this ring is a massless ring. So there is no weight acting. What are the forces acting? One force is tension, that is acting in the downward direction, and this tension will be T1 because this is a massless chain. So each point of this chain will have same tension, and the value of this tension will be T1, and that's why on this ring in the downward direction a tension force will be acting, and that magnitude will be T1. Similarly, this chain will apply a force in this direction, and this tension will be T2. Now assume that this chain remains horizontal, and that's why we can show tension force in a horizontal direction. Another force that will come from this chain, and that has a magnitude of T3. So these are the three forces that is acting on this ring. Now let us call this as x-axis and this as y-axis. So this is the positive direction of x-axis, and this is the positive direction of y-axis. Now if you see, this angle is 60 degree. This means this angle is how much? This angle is also 60 degree. So we can show this angle. This angle is theta, and theta is equals to 60 degree. Now these two objects are in equilibrium. So we can write equilibrium equations, that is we can apply Newton's first law. So let us apply Newton's first law in this case for these two objects. So first we can consider equilibrium of engine. So equilibrium of engine. So now what are the forces that is acting? In this case there is no horizontal force. So if I consider horizontal force component of all horizontal forces summation 0, this does not give anything because in the horizontal direction in this case nothing is acting. Now if I consider summation of all the forces in the y direction is equals to 0, this will give me vertical direction I have a force T1, and the downward direction, this is a upward direction, that's why we have taken positive. Now downward direction we have a force W, and that is a negative because this is in the downward direction. So this gives me tension T1 is equals to W. So we calculated one part, that is T1 is equals to W. Now next what we can do is we can consider equilibrium of ring. So let us consider equilibrium of ring. So what are the equation we can write? If I write summation of fx is equals to 0, this will give me forces in the x direction. So what are the forces that is acting in the x direction? This force, that is T3, has two components, one component along this axis and other component along this axis. So in this direction you will have T3 cos theta, and along this axis, that is y-axis, you will have T3 sin theta, where theta is equals to 60 degree. Now so what are the forces that is acting in the x direction? T3 cos theta, that is positive, and T2, that is negative. So let us write in x direction T3 cos theta minus T2 is equals to 0. So this is the equation in the x direction. Similarly, I can write equation in the y direction. So by direction I can write summation of Fy is equals to 0. So this will give me what are the forces that is acting in the by direction. T3 sine theta, that is positive, and T1, that is negative. So I can write T3 sine theta minus T1 is equals to 0. So let us write this. T3 sine theta minus T1 is equals to 0. So now I know T1, so I can calculate T3. So from, let's call this is equation 1, this is equation 2. So from 2 I can write T3 is equals to T1 divided by sine theta. And theta is equals to 60 degree. So this is simply T1 divided by sine 60 degree. And sine 60 degree is root 3 by 2. So this will be T1 divided by root 3 by 2. So this is 1.2 W. So we calculated T3, that is nothing but 1.2 W. Finally, I can use equation 1. So if I use equation 1, I can calculate T2. So T2 is how much? T2 is simply T3 cos theta. And now I know T3. T3 is basically T1 divided by sine theta. So T1 divided by sine theta and then multiply by the cos theta. And in this case, I know cos theta, basically theta equals to 60 degree and T1 is equals to W. So we can write W cos 60 degree and this divided by W. So not W, simply sine 60 degree. Now if you plug all this value, you can find T2 is equals to 0.58 W. So this is value of T2. So we have solved for T1, T2 and T3. So T1 is equals to W. So we can write here T1 is equals to W and T2 is equals to 0.58 W and T3 is equals to 1.2 W. I can show all this in a free body diagram. You remember, if you draw free body diagram for ring, you have T1 in the downward direction, which is equals to W. You have T2 that is in the horizontal direction, and this is nothing but 0.58 W. And then you have T3 at an angle of 60 degree, this is 1.2 W. So a few important points in this case. The maximum value of tension occurs in chain 3, that is 1.2 W. So if there is a chance of breaking of any chain, then chain number 3 will break first because it has maximum tension. And also the tension T3 is greater than W, that is 1.2 W. So little bit greater than 1.2, little bit greater than W. This is because this T3 is balancing T1 as well as T2 both, and that's why this is greater than W, because it also has to take care of T2. So in this video we learned how to calculate or how to write equation in case of two-dimensional object. You have to basically see how many unknown you have, and then correspondingly you have to think of how many equations you are going to write. For that purpose you have to divide your system into different components and you have to write equation or equilibrium equation for each component, and subsequently you have to solve the equation to get the unknown or target values. I hope you like this video. If you like, please share with your friends, like and subscribe. I will see you in the next video. Thank you for the time being. Hello friends, in the last video we have seen how to apply Newton's first law in case of two-dimensional equilibrium, and we have applied for a Cartesian coordinate, that is horizontal and vertical. So we have written two equations, one along the x-axis, another along the y-axis, and we solve for unknowns. Now in this session we will see how to apply two-dimensional equilibrium equation for Newton's first law in case of an inclined plane. So let us discuss all this using a problem. So this problem says a car of weight W rests on a slanted ramp attached to a trailer. So this is the trailer and this is the car and this is the ramp. So this car is resting on this ramp and this is attached to a trailer by a cable. So only a cable running from the trailer to the car prevents the car from rolling off the ramp. So this is the only cable that basically supports rolling of the car from this ramp. So all the forces is taken by this cable only. There is no any other force that is acting in this system. This means you have to ignore the friction between tire and the ramp. So there is no friction between tire and the ramp. No friction between tire and the ramp. It is also said the car's brake are off. So car is not the car is not applying any brake. So car brake is off. And its transmission is in neutral. So your car can be a forward gear or it can be a backward gear or it can be in neutral gear. So this car is in neutral gear. Now we have to find the tension in the cable. So this cable, what is the tension we have to find? Let's call this tension is T. And we have to find the force that ramp exerts on the car's tire. So what is the force that ramp exerts on the car's tire? That we have to find. Basically in this case, ramp will exert a force that is normal to the this ramp, and similarly here also we will have some normal force. So what we will do is we will club all these two normal to a single normal and we will call this as a normal force N in this case. So we'll say only a single normal force is acting in this direction. So we have to find this normal force. So in this case there are two unknowns or two target variables. So what are target variables? So target variables in this case is tension in the cable and normal force applied by the ramp. And in this case we will assume there is no friction between tire and the ramp. So we will assume there is no friction. So there is no friction. So there are two unknown, that is two target variables, and we have to solve. So this means at least we need to have two independent equations. So what is required in this case? We require two independent equations. So we require two independent equations. Now how do you write equation? The first step is to draw the free body diagram. So let us draw the free body diagram of this car. So what are the forces that is acting on this car? The first is weight of the car that will act in the downward direction. So let us denote this car using a point, and there is a weight that is acting in the downward direction. What other forces are acting? So let's say this is my ramp. So this dotted line shows the ramp and this is the horizontal line that makes an angle alpha. And on this car, what are other forces? One is normal reaction, because on this tire we will have a normal reaction, on this tire we will have a normal reaction. But what we are saying is we are basically combining all these normal reaction and we will show only one normal reaction. So this normal reaction will somewhere here. Now this normal reaction will be perpendicular to the ramp. So this is a normal reaction and the direction is perpendicular to this ramp. What other forces is acting? You have this cable. So this cable is applying tension force T. So there is a force that is acting in this direction and this force is due to the cable and the magnitude of this force is T. Is there any other force that is acting? So you check. Before proceeding further, you have to check whether any other forces are acting on this system or not. That is on the car. No other forces. Let us think about friction. As I said earlier, there is no friction. We are assuming that there is no friction. So friction is also absent. So we are making an assumption that is there is no friction in this case. Tire and ramp, there is no friction between tire and ramp. Now we have to solve for normal reaction and tension. You can solve this problem in either Cartesian coordinate, that is horizontal x-axis and vertical y-axis. But to simplify the problem, there is another approach. What we can do is, we can think of x-axis in this direction. That is, my x-axis is parallel to the ramp, that is parallel to inclined plane. And y-axis will be perpendicular to this ramp. So y-axis will be in this direction. So this is my y-axis and this is my x-axis. So now this angle is how much? This angle is alpha, then this angle will also be alpha. This I said many times. There is a theorem in mathematics that says angle between line is equals to angle between perpendiculars. On this line, this is the perpendicular, and this line, this is the perpendicular. So this angle is basically alpha. So this angle is alpha. So now I have to break, or I have to take the component of forces along x and y direction, and then I have to write equilibrium equations. So what will be the component of W in this direction? So in this direction, this angle is alpha, so this will be W cos alpha. And what about in this direction? In this direction, W will have a component that is W sin alpha. Let us put a bigly sign here on this W to show that now this W has been resolved in W cos alpha and W sin alpha, and whenever we are writing equation, we don't have to consider this because we have already taken the effect of this W as two components, W sin alpha and W cos alpha. We don't have to take the component of tension because tension is along the x-axis and normal reaction is along the y-axis. So we don't have to take the component of tension and normal reaction. This is the advantage of using this coordinate. The coordinate x is along the parallel, that is along the incline, and y is along the perpendicular to the incline. So this is one of the major advantages. We will later see what happens if you take Cartesian coordinate. But before that, let us try to solve this problem. So this is a two-dimensional equilibrium. There are two unknown. We have to write two equations. First, we will write equation in the equilibrium equation along the x direction. So what are the forces that is acting along the x direction? Tension, that is a positive, and then I have to consider this W sin alpha that is acting in the negative x side. So we have to write minus W sin alpha. And sum of all the forces is equals to 0 because this car is in equilibrium. So from here I can say T is equals to W sin alpha. So we have solved for T, and W is known, alpha is known, so we can calculate T in terms of W and alpha. Similarly, we can write equation or equilibrium equation along the y-axis, and we can write sum of all the forces along the y-axis is equals to 0, and this will give me normal reaction that is along the y-axis, so this will be a positive quantity, plus W cos alpha that is along the negative direction of y-axis. So we have to write minus W cos alpha, and sum of these two forces is equals to 0. From here I can write N is equals to W cos alpha. So now we have calculated two unknowns, that is tension and normal reaction. Now consider a special case of alpha. So let's say two special cases we can consider. First is alpha is equals to 0 degree. So when alpha is equals to 0 degree, what will the value of t? Sine alpha, sine 0, that is 0. So this is t is equals to 0. And what will be the value of normal reaction? Normal reaction will be w cos 0, that is equals to w times 1. So this is equals to w. So when alpha is equals to 0 degree, this means what? This means your car is simply resting on a horizontal plane. So your car is resting on a horizontal plane and this cable is simply attached. So in this case, this makes sense because this cable is not going to take any tension, and that's why this tension is 0. And all the forces, that is normal reaction, will take all the forces, that is the weight. So normal reaction will be equal to the weight. So in case of alpha is equals to 0 degree, this makes sense. Now what about if alpha is equals to 90 degree? Alpha is equals to 90 degree. In that case, t will be, because t is w sine alpha. Sine 90 degrees is 1, so t is equals to w. And what about n? In this case, n will be cos 90 is 0, so this is 0. Now how this will look? If alpha is equals to 90 degree, this means your car is hanging something like this. In this case, you can expect, because this is not touching to the plane, or you can say this is simply touching your plane, inclined plane will become something like this. So in this case, all the weight is taken by the tension. So in this case, you can say tension is equals to W, and normal reaction, because this is just a parallel plane, it is not applying a force perpendicular to the this car. That's why normal reaction will be 0 in this case. So these two special cases are sometimes useful to check whether the answer that you have got is right or not. Sometime in objective question you can use this as a trick. You can put this as special cases and you can find the answer directly. Now if you want, you can solve the same problem in Cartesian coordinate also, but that will basically increase your calculation. So let us try to illustrate this. So what we will do is, we will solve this problem using Cartesian coordinate, just to illustrate how the complication arises, how the calculation increases. So this is your car and the forces acting is W, and in this direction you have tension force, and this is the normal reaction, and this is your inclined plane, and this angle is alpha. Now if this angle is alpha, then this angle is also alpha. Now this is, let us put this somewhere here. So this is my x-axis and this is my y-axis. So if this angle is alpha, then this angle is 90 minus alpha and this angle is alpha. You can prove yourself. Now if I want to solve this problem in xy coordinate as shown in the figure, that is the Cartesian coordinate. Now what I have to do is, I have to break. I have to take the component of the forces along the x-axis and along the y-axis. So this is my x-axis and this is my y-axis. So what are the forces that I have to take the component? First component of t along this axis, this will be t cos alpha, and along this axis I will have t sine alpha, and now I can make a bigly sign over this. This means now this has been considered. Similarly, I have to take the component of n. So along this side I will have n cos alpha. So this angle is alpha, so this will be simply n cos alpha, and along this direction I will have n sine alpha. So this is n sine alpha. So this is n sine alpha. And we can make a bigly sign over here so that to understand that this has been taken into account. Now let us write equation of motion. But before that, you see, we have taken component of normal reaction, and also we have taken component of tension along the x-axis and along the y-axis. This increases the calculation because you see in the previous case you have to take the component of only one force, that is W. In this case you have to take the component of two forces, normal reaction and tension. But still we can solve this problem. So summation of Fx is equals to 0, that is the total forces acting along the x-axis is equals to 0 because object is in equilibrium. So along the x-axis we have t cos alpha, and then we have n sin alpha, that is negative side of the x-axis. So this becomes minus n sin alpha, and then this is equals to 0. So from here I can write t cos alpha is equals to n sin alpha. So this is my equation number 1. Similarly, we can write equilibrium equation along the y-axis, that is summation of Fy is equals to 0. So what are the forces that is acting along the y-axis? One force is n cos alpha and t sin alpha, that is along the y-axis and it is positive. So we can write n cos alpha plus t sin alpha, and then there is a force that is acting along the negative direction of y-axis. So this is minus W, and sum of all the forces is equals to 0. So from here I can write n cos alpha plus t sin alpha is equals to W. So this is my equation 2. Now from equation 1, let us eliminate, we can eliminate n. So we can write n is equals to t cos alpha divided by sin alpha. So from 1 I can write n is equals to t cos alpha and this divided by sin alpha. So let us plug this in equation 2. So I can write n cos alpha. So basically I have to write n. So n is nothing but t cos alpha divided by sin alpha multiplied by cos alpha plus t sin alpha is equals to W. Furthermore, I can write t cos square alpha plus this will become t sin square alpha, and this divided by sin alpha. This is equals to W. And now we know that cos square alpha plus sin square alpha is equals to 1. So this is simply t divided by sin alpha is equals to W. So from here I can write t is equals to W sin alpha. So I know t. Similarly, if I plug into this equation, I can get n. N is nothing but t is W sin alpha and then multiplied by cos alpha divided by sin alpha. So n is basically W cos alpha. So here I can write n is equals to W cos alpha. So this is W cos alpha. So you see, we can solve the same problem using a Cartesian coordinate. But the problem is, in this case, calculation becomes lengthy and unnecessarily there is a chance of mistake that increases. So it is always advisable to consider an inclined plane problem into a axis that is perpendicular to the inclined plane and another axis that is parallel to the inclined plane. I hope you have liked this video, and if you like this, please share and like. Also, you can comment in the comment box, and I will see you in the next video. Thank you. Hello friends. In this video, we will learn about how to apply Newton's first law when the object is moving with a constant velocity over an inclined plane. So the objective of this session is to analyze equilibrium of bodies connected by cable and pulley. And this we will illustrate using a problem. So this problem says block of granite are to be hauled up a 15-degree slope out of a quarry. So this is block of granite and this has to be hauled up. And the dirt is to be dumped into the quarry to fill up the old holes. And the dirt whatever we have, and this dirt has to be pulled down and it has to be filled into the old holes. To simplify the process, you have to make some assumption. And what is the assumption and what is the design you are going to make? You design a system in which a granite block on a cart with a steel wheels, weight W1 including both cart and block. So the weight of cart and block is given. So this is and on a steel rails also. So all this has a weight of W1. So wheels is a steel wheels and the weight of cart plus wheel plus this granite block, all this comes out to be W1. And this is to be pulled up a hill on a steel rails by dirt filled bucket. So this is going up on a steel rails, and how this goes, and this goes because of this bucket that is filled with the dirt. Weight W2 including both dirt and the bucket. So the weight of bucket plus dirt is given, that is equals to W2. That descends vertically into the quarry. So this bucket plus dirt system descends into the quarry. How must the weight W1 and W2 be related in order for the system to move with a constant speed? So our target variable is to find what is the relation between W1 and W2 so that this system moves with a constant velocity. So this is given, that is moving with a constant velocity. Ignore friction in the pulley and wheels and ignore weight of the cable. So you have to make some assumption, that is ignore any kind of friction and ignore weight of these cables also. So how will you solve this problem? So first you have to make an initial setup, and that is what are the things that is given. So you have been given this angle, let's call this angle as theta. So theta is given, this is equals to 15 degree. Weight W1 is given and this weight W2 is given, and it has been given that is this system is moving with a constant velocity. This means this is in equilibrium. So we can apply Newton's first law. If system is in equilibrium, the sum of total forces is equals to 0 on a bucket as well as on the cart plus granite block system. So the idea to solve this problem is first we have to idealize. That is, this is my system and I have to make some idealization. And then I will draw the free body diagram. We will draw free body diagram for cart, that is block plus cart system, and another free body diagram we will make for bucket, that is W2. And then we will write equations. And once you have this equation, we can solve this equation, then we can find what is the relation between W1 and W2. So this is the idealized system. So I can show this cart plus granite block something like this and the bucket something like this. And this is the idealized system, and then I can assume there is a pulley and this is connected, the cables are connected and passing over the pulley. So I have to draw the free body diagram. So let us first show this cart plus granite. So I am showing this here. So this is the free body diagram of cart. So let us first draw free body diagram for cart. So what are the forces that is acting on this cart? The first force that is acting is weight, that will act in the downward direction, and this is W1. Now this rail will apply a normal reaction that is perpendicular to the incline, and this normal reaction is N. Since there is no friction, we can say there is no friction force acting along the parallel direction of the incline, but this is trying to pull this. So there is a tension force that is acting in this direction. So a tension force that is in the cable that will act in this direction. So this is my tension force, this is my W, and this is my normal reaction that is acting on the cart plus block system. Now similarly, I can draw free body diagram for the bucket. So let us draw free body diagram for bucket. So this is my bucket. I can show using a point mass. And what are the forces that is acting on this bucket? The first force acting in the downward direction is its weight, that is W2. And this cable is trying to pull this up. So there is a force that is acting in the upward direction, that is tension T. Remember, this tension and this tension is same because we are assuming that this is a cable that has no mass. That is massless cable, massless string. So whenever you have a massless string, you will have same tension throughout the string, and that's why this tension is T at this point of time also. So how will you solve this problem? Before solving this, you have to first resolve the component along the incline and perpendicular to the incline. So you remember, whenever we solve problem on inclined plane, what we do is we resolve or we take the components of forces along the inclined plane and perpendicular to the inclined plane. So we have to take something like this. So this is the direction perpendicular to incline, and this is the direction that is along the incline. So let's call this as the x-axis, and this is my y-axis. So I have to resolve this forces. Now this angle is 15 degree, so this angle will also be 15 degree. You can basically prove. So this angle is 15 degree. So W1 will have one component in this direction, and that will be W1 cos 15 degree. Now another component of W1 will come in this direction, and that will be W1 sine 15 degree. Now we don't have to consider this now because we have taken the component, and that's why we are making a bigly sign. Now we have our free body diagram ready. Now this system is in equilibrium. So we can write Newton's first law. Let us first write for bucket. Now in the bucket, there is no force that is acting in the x direction. So this is my x direction, and this is my y direction for bucket. So on bucket, only forces are acting in the y direction. So what are the forces? In the upward direction we have force T, and the downward direction we have W2. So this is downward direction, that's why we have to take a negative sign. And sum of all the forces is equals to 0 because this system is in equilibrium, because this is moving with a constant velocity, acceleration is 0, and this is basically an equilibrium situation from the Newton's first law. So from here I can write T is equals to W2. So let us call this as equation 1. Now similarly I can write equation for cart. So let us write equations for cart. So what are the forces that is acting on the cart? First let us write along the x direction, that is summation of fx is equals to 0. So this will give me the forces along the x direction. One force is acting along the x direction is T, and the negative x direction is W1 sine 15 degrees. So this will be negative, that is W1 sine 15 degree. And once again, sum of these forces is equals to 0. So this is one equation. Similarly, I can write another equation, that is summation of Fy is equals to 0, and this will give me the forces along the bidirection. Along the bidirection we have normal reaction plus, and this force is along the negative bidirection, that is minus W1 cos 15 degree. So this is equals to 0. So this is my equation 2 and this is my equation 3. So from equation 2 I can write, from equation 2 I can write T is equals to W1 sine 15 degree. And now if you remember, what is my target variable? My target variable is to find a relationship between W1 and W2. So now from this, that is equation 1, I can equate T. So this is T is equals to W1 sine 15 degree and which is same as equals to W2. So I can write W2 is equals to W1 sine 15 degree. So this is the relation between W1 and W2, so that this system will move with a constant velocity. If you put the value of sine 15 degree, you can write W2 is equals to 0.26 W1. So W2 has to be equals to 0.26 W1 so that this system will move with a constant velocity. We have another equation, that is equation number 3. This equation will give you the normal reaction. So if you want to calculate normal reaction, you can write normal reaction is equals to W1 and this is cos 15 degree. So this is cos 15 degree. So this reaction will be helpful to calculate the normal reaction that is acting on this block, granite block and cart system. So one important point, this analysis basically does not account for the direction of motion. That is, your bucket can either go in the downward direction or it can go in the upward direction. What I mean, this means this system can either move in this direction, or even if this system is moving in this direction, you will have same relationship. That is, this does not account for the direction of motion. So when you have W2 is equals to 0.26 W1, it can move in both directions, either up or down. So this is the situation when we have W2 is equals to 0.26 W1. This can move either up or it can also move either down. So I can show something like this. This can move up or it can also move down. For both directions, this is satisfied. Now what will happen if W2 is greater than 26% of W1? In this case, what will happen? So this is W2 and this is W1. So W2 is greater than 26% of W1. So this means this side is heavy. So this means this whole system will move up. So this case you can say this system will move up. Now what will happen if W2 is basically less than 26% of W1? This means this time this is lighter and this whole system will move in this direction and the cart will go in the downward direction. So I can say in this case this will move, the cart will move in the downward direction. So to summarize, if you have W2 is equals to 26% of W1, in that case cart can move either up or cart can either move downward direction. If W2 is greater than 26% of W1, in that case cart has to move in the upward direction. And finally, if W2 is less than 26% W1, in that case cart will move in the downward direction. So in this video we learned how to apply Newton's first law when the object is moving with a constant velocity over the inclined plane. Hope you like this video, and if you like, then please share with your friends and among your colleagues, and I will see you in the next video. Thank you. Hello friends. In last few videos we have seen how to apply Newton's first law, and we have seen different cases like horizontal plane, inclined plane, and all these cases how we apply Newton's first law. Now from this video onwards, we will be going to discuss Newton's second law and we will learn how to apply Newton's second law in different situations. So the objective of this session is to analyze the straight line motion with a constant force. So this is a relatively simple situation when you have a motion in the straight line and you are applying a constant force. Let us illustrate this case using a problem. So this problem says an ice boat is at rest on a frictionless horizontal surface. So this is the ice boat and this is on the rest on a horizontal surface which is frictionless. So friction coefficient is given and this is equals to 0 in this case. Now the question says a wind is blowing along the direction of the runner so that 4 seconds after the ice boat is released, it is moving at a speed of 6 meters per second. So wind is blowing in this direction and this wind will basically apply a force to this ice boat and basically it will accelerate the motion of this ice boat. So this question is saying this ice boat starts its motion at t is equals to 0 and after 4 seconds this ice boat has gained a speed of 6 meters per second. In other words, from a start after 4 seconds it has reached or it has gained a velocity of 6 meters per second. So basically there is an acceleration from 0 to 6 meters per second. So velocity is changing. So there is acceleration of velocity. Now the question says what constant horizontal force does the wind exert on the ice boat? So this wind is basically applying a force. Let's call this as a constant force. Let's call this as Fw, the force due to the wind. So we have to basically calculate this wind force. The combined mass of ice boat and the rider that is given and this is 200 kg. So mass is given of boat plus rider. So how will you solve this problem? So first we have to see what are the things that is given. So what are the things that is given? So it is given after t is equals to 4 seconds, it has gained a speed of, so let's call initial speed is 0, that is sometime we write with u, the initial speed with u. So u is equals to 0, that is initial speed is given. And the final speed after 4 seconds that is also given, that is 6 meters per second. Any other thing that is given? Yes, mass is given. Mass of rider plus ice boat, this is equals to 200 kg. And we have to find Fs. So the target variable in this case, that is force applied by the wind, that is Fw. So this is the term that we have to find. So how will you solve this problem? So what we will do first, we will first draw the free body diagram. And once I have the free body diagram, we can apply Newton's second law. That is Newton's second law. Why we are going to apply Newton's second law? Because you see, the hint is given. We have to find force. And the question also gives a hint of acceleration. Because the velocity is changing, we can calculate the acceleration. And we know the Newton's second law basically relates force is equals to mass into acceleration. So I have to calculate this force and I have been given this acceleration and this mass. So now I can calculate my force. So in this case, basically I have to apply Newton's second law. So let us first draw the free body diagram of this ice boat system. So what are the forces that is acting? The one force, that is the weight that will come in this direction. So let us show this using a point mass and the weight is acting in the downward direction and the magnitude of this weight is mg. Now this surface will also apply a normal reaction. Basically there are two places we will have, that is the normal reaction. We will concentrate all this normal reaction at one point and we will call this normal reaction as N. So this is the normal reaction that is acting on this ice boat system. Now the wind is also applying a force and the magnitude of this is Fw. So we can show the wind force something like this. And now we can consider my x-axis along this direction and my y-axis along this direction. So this is complete for free-body diagram. Now we can use force is equals to mass into acceleration to calculate the force, but to calculate acceleration we have to use kinematical equation. So this is a constant force, so acceleration will also be constant because this force is constant, so acceleration will also be constant, and we can apply kinematical equation, that is V is equals to U plus AT. You may remember this equation where V is the final velocity, U is the initial velocity, A is the acceleration, and T is the time in which velocity basically changes from U to V. So the final velocity in this problem is given, that is 6 meters per second, and initial velocity is 0, and we have to find acceleration, and time is given, this is 4 seconds. So from here basically I can calculate acceleration is nothing but 6 by 4 meter per second square, and this is 1.5 meter per second square. So once I have this acceleration, I can calculate the force. So let us apply Newton's second law in the x direction. So I can write in the x direction total force. So I can write Newton's second law in x direction. So in the x direction, what are the forces that is acting? Fw is the force. Force is equals to mass into acceleration. So mass is given, that is m, and acceleration now I know that is 1.5 meter per second square. So if you plug the value of mass, which is basically 200 kg in this case, so 200 kg times 1.5 meter per second square. So if you calculate this, this will turn out to be 300 Newton. Basically kg meter per second square is called Newton. So 1 kg, so we are using the conversion, that is 1 kg into meter per second square. This is equals to 1 Newton. If you want, you can also write equation in the bidirection. So in this case, bidirection forces are N and mg is negative. So I can write in this case N minus mg, and the vertical direction there is no acceleration, so this is equals to 0. So now I can write N is equals to mg. So if you want to calculate normal reaction, you can use this equation also. So in this video we have learned how to apply Newton's second law, and we illustrated this with very simple situation in which you are applying a constant force so that the acceleration is constant, and then you can basically simply use force is equals to mass into acceleration to calculate the force. I hope you enjoyed this video, and if you enjoyed, please share with your friends, and I will see you in the next video. Thank you. Hello friends. In the last video we have seen how to apply Newton's second law when there is no friction present. Now in this video we will see how to apply Newton's second law when the friction forces are also present. So the objective of this session is to analyze the straight line motion with friction, and this we will illustrate using a problem. This problem we have already done without the friction force. Only the difference in this problem and the previous problem that we have done in the past video, there is a friction force in this case. So the problem says, suppose a constant horizontal force with magnitude of 100 Newton opposes the motion of the ice boat. This is a constant horizontal friction force. This opposes the motion of the ice boat as shown in the figure. So this is the ice boat and he is the rider, and this ice boat is moving in this direction, and there is a friction force between this surface and this ice boat that tries to oppose the motion of this ice boat. So this is acting in this direction and the magnitude of this is 100 Newton. Let's call this as a small f that is given in the problem. In this case, what constant force Fw must the wind exert on the ice boat to cause a constant x acceleration, that is x is equals to 1.5 meter per second square. So what is happening in this case? Basically wind tries to apply a force. Let's call this force as Fw, that is force due to the wind. And this force will accelerate the motion of the ice boat. And finally, basically at t is equals to 0, this ice boat just starts its motion, that is initial velocity is 0, and after a certain point of time it gains an acceleration and the value of acceleration is given, that is 1.5 meter per second square. So we have to find what is the magnitude of wind force, and this is constant magnitude. So this is a constant wind force. The combined mass of ice boat and rider is given and this is 200 kg. So how will you solve this problem? So let us first write what are the things that is given. So what are the things that is given? We have been given friction force magnitude, that is 100 Newton. Mass of ice boat plus rider, that is given, that is 200 kg. And we have been given the final acceleration in the x direction, that is 1.5 meter per second square. And we have to find the Fw, that is force due to wind. So how will you solve this problem? Hint comes because you have to find force. And what are the things that is given? You have been given acceleration, mass. This all gives an idea, that is we are going to apply Newton's second law. So that is we have to apply Newton's second law and then we have to write equation and then we have to solve. But before that, for applying the Newton's second law, I have to draw the free body diagram. So in this case, this will be the flow chart for doing this problem. I have to first draw the free body diagram. And once I have the free body diagram, I have to use Newton's second law, that is writing equations. So Newton's second law. So once I have equations, now I can solve this equation and I can basically get the unknowns. So then you have to solve the equations. So let us first draw the free body diagram. So this is my ice boat and rider. So what are the forces that is acting? One force that is obvious is weight that is acting in the downward direction, that is nothing but mg. So let us denote this ice boat plus rider as a point mass and the forces are acting in the downward direction is mg. Normal reaction will come from here and come from here, but we will consider all the equivalent normal reaction that is passing through this point and the magnitude of this normal reaction, let's call this as n. So this is normal reaction. So this is my y-axis. So this is my y-axis. Similarly, now we can assume this is our x direction. So this is x-axis. What are the forces that is acting along the x direction? One force that is acting this due to the wind, that is Fw. So we can show this force Fw something like this. Friction forces are also acting, but friction forces act in the opposite direction of the motion. Friction force always tries to oppose the motion. So this is moving in this direction, so friction force will act in this direction. So in this case, the friction forces are acting in this direction and this will act at the point of contact between the ice boat and the horizontal plane. So this force will act in this direction and the magnitude is F. Now once I have the free body diagram, I can write equation of motion. So let us first write motion equation in the x direction, that is summation of all the forces in the x direction is nothing but mass times acceleration along the x direction. So what are the forces that is acting in the x direction? One force is Fw, that is positive side of the x direction, and friction force that is in the negative direction, so this is minus F, is equals to mass times acceleration. So if you plug all this value, we can calculate magnitude of force due to the bend. So we can write Fw is equals to F plus max. Friction force is given, that is 100 Newton, mass is given, that is 200 kg, and acceleration is nothing but 1.5 meter per second square. So if I plug all this will come 400 Newton. So the magnitude of force that is applied by the bend is equals to 400 Newton in this case. You can also find normal reaction if you consider equation in the y direction. That is, in the y direction there is no movement, there is no acceleration. So we can say summation of all the forces along the y direction is equals to 0. This means in the y direction is normal that is acting, and the mg is acting in the downward direction, that is minus mg is equals to 0. So this gives you n is equals to mg. Now if you compare, we have done the same problem, but there was no friction. In that case we found the Fw value was 300 Newton. You can see in the previous videos. So in that case, when F was 0, that is there is no friction, in that case Fw was 300, and when there is a friction of magnitude 100 Newton, we found that Fw is equals to 400 Newton. This makes sense. If the friction is present, bend has to apply more force, because some of the force of the bend, that is the force applied by the bend, is resisted by the friction. And how much this resistance is? This much resistance is 100 Newton, and that's why the difference between these two forces is 100 Newton. So you see, if you have a friction, you have to apply more force, the bend has to apply more force. I hope you enjoyed this video, and if you enjoy, please share, like and subscribe this channel, and hope I will see you in the next video. Thank you. Hello friends, in the last video we have seen how to apply Newton's second law in case if the friction is present. Now in this video we will see how to solve the problems related to elevator. So the objective of this session is to find tension in an elevator cable, and this we will illustrate using a problem. So this problem says an elevator and its load have a combined mass of 800 kg as shown in the figure. So this is the elevator and we have some load inside this elevator. So the total mass of load plus elevator is given, that is 800 kg. The elevator is initially moving downward at a speed of 10 meter per second. So this elevator is moving in the downward direction, and the speed is given, and this speed is 10 meter per second. It slows to a stop with constant acceleration in a distance of 25 meter. So this elevator comes to rest, and before coming to rest it covers a distance of 25 meter. This means to bring this elevator into rest, this cable has to apply some force in terms of tension. So the question says, what is the tension T in the supporting cable while the elevator is being brought to the rest? So we have to find what is the tension in this elevator that is applied before this elevator comes to the rest. One important point in this case, you can think this tension has to be greater than mg, that is the weight of the lift, because this tension has to decelerate the elevator. So to decelerate the elevator, it has to apply more force than mg. So one can expect that the final answer of tension should be greater than mg, and that we will see towards the end of this session. So how will you solve this problem? So first, what are the things that is given? So we have been given mass, that is 800 kg, mass of elevator plus load. A speed is given, initial velocity is given, that is 10 meter per second, and this speed is in the downward direction. So U denotes initial speed. Now this elevator has covered a distance of 25 meter before coming to the rest, and this distance is also in the downward direction. And the question says the acceleration is constant. So we have a constant acceleration. So this is a constant acceleration case. So when you have constant acceleration, you can apply kinematical equation, that is v is equals to u plus at, or v square minus u square is equals to 2as. These equations you can apply because these equations are valid only for case of constant acceleration. And what we have to find? We have to find tension. Tension in the cable, that is my target variable. So now how will you solve this problem? So idea is, you see, you have been given initial velocity, and basically you also know the final velocity. The final velocity is 0 meter per second because the elevator comes to the rest. So once you know the initial velocity and the final velocity and the displacement covered, then you can use kinematical equation to calculate deceleration, or you say acceleration with a negative sign, whatever the sign we will discuss later. So you can calculate acceleration. So once you know the acceleration, you can use Newton's second law to calculate the forces, that is in this case tension forces. But to apply Newton's second law, you have to draw the free body diagram. So what is the flow chart for doing this problem? So first you have to calculate acceleration. So this is your first thing that you have to do, and once you know the acceleration, you can basically draw free body diagram. In this case, free body diagram of elevator, and then you can use Newton's second law to write equations. So you will have some equation, one in the x direction, one in the y direction. In this case, x direction equation will not be useful. So only one equation, because we need to have only one variable. So we'll write one equation, and that is in the y direction. And once I have equation, we can solve to get the target variable. So first thing is to find acceleration. So how will you find acceleration? So you have to use a kinematical equation, and in this case we will use v square minus u square is equals to 2as. So you may remember this formula, v square minus u square is equals to 2as, where v is the final velocity, u is the initial velocity, a is the acceleration, and s is the displacement covered. Now in this case we need to have a sign convention also. So let us assume the positive direction is the upward direction. Now if you consider this, what is the sign of u? Basically u, the initial velocity is in the downward direction, so u will be negative. So you can say u is basically equals to minus 10 meter per second. And the elevator is also going in the downward direction, so s is also negative in this case. So I can say s is equals to minus 25 meter. So now I can use this in this formula to calculate acceleration. The final velocity is 0. So this will be 0 square minus u is minus 10. So this square is equals to 2a. S is nothing but minus 25. So from here you can write a is equals to, this is minus 100, and this divided by minus 50. So this will be 2 meter per second square. So you see the acceleration is positive, and this is 2 meter per second square, and positive sign makes sense because if acceleration is positive, this means elevator will come to the rest, because this is acceleration that is in the upward direction and the elevator is moving in the downward direction. So this acceleration will try to decelerate the elevator, and finally the elevator will come to the rest. Now once I know this acceleration, now I can draw the free body diagram. So what are the forces that is acting on this elevator? One force that is acting, that is weight, that is mg. So let us show this elevator using a point, and the force is acting is mg, that is acting in the downward direction. What other force? The force due to this cable is tension, so this force will come in the upward direction. We are assuming there is no friction present between these two, that is the rail, that is a steel rail, and the elevator ball bearings. All these are smooth and there is no friction present at the surface of contact between the rail and the elevator. So this is the assumption that we are making. So now I can write Newton's second law, that is sum of the forces in the bidirection is equals to mass into acceleration in the bidirection. In this case, acceleration is in the bidirection and the magnitude is 2 meter per second square. What are the forces? In the upward direction we have a force of T, and in the downward direction we have a force of mg. So there is a negative sign, and m, and acceleration is given, that is nothing but 2 meter per second square. Or you can simply write acceleration and then finally we will put the value. So let us write this is a. So from here I can write T is equals to mg plus a. So you can see the tension force is greater than mg. So we can basically calculate this tension is m is at 100 kg and g in this case is 9.8 meter per second square, and acceleration is 2 meter per second square. So if you calculate this T is equals to 9440 Newton. So this is the tension force that you have in this case. Now see, if you calculate the value of mg, so mg will be 800 kg, and this is kg and g is 9.8 meter per second square. So this will be 7840 Newton. So this is the value of mg. So you see, in this case tension is greater than mg, and that we said in the beginning also that in this case tension has to be greater than mg, because this cable has to apply a force so that the elevator should decelerate. This means, in other words, this elevator will have acceleration in the upward direction so that the accelerator can decelerate, and that's why the tension force is greater than mg. You will also get the same answer, that is the value of tension, if the elevator is moving up and gaining a speed of 2 meter per second. That is the acceleration is 2 meter per second square. So you should get the same T value if your elevator is moving up and the acceleration in this case is 2 meter per second square. So you will get the same answer. So you can try yourself. That is, for this case you also get tension equals to mg plus a. So in this session we learned how to apply Newton's second law in case of elevator, and how to find tension in case of in a cable when the elevator is going in the downward direction and it is decelerating and finally it comes to rest. Initial velocity is given. Then you use kinematical equations and Newton's second law to find the tension in the cable of the elevator. I hope you have liked this video, and if you like this video then please share with your friends, and I will see you in the next video. Thank you. Hello friends, in this video we will continue our examples on Newton's second law, and we will study one more dimension, that is how do you calculate apparent weight inside an elevator, and this we will illustrate using a problem. So this problem says the elevator as shown in the figure is moving down with a deceleration of 2 meters per second square, that is decreasing the speed. So we have an elevator and this elevator is moving in the downward direction and this is experiencing a deceleration and thus that value is given, that is 2 meters per second square. In other words, this elevator is going to be slow and finally this is going to come into the rest. So this is a decreasing the speed. So magnitude of acceleration is given, that is 2 meters per second square. A 50 kg bowman stands on a bathroom scale while riding in the elevator. So C is inside the elevator and there is a bathroom weighing a scale basically, and C rides on this weighing scale. So what is the reading on the scale? So we have to find the reading on this weighing scale. So what are the things that is given in this case? So first thing that is given, that is the mass of bowman, that is 50 kg, that is given. And acceleration value is also given, that is 2 meters per second square. And we will see later the direction of this acceleration also. For the time being, the magnitude of acceleration is 2 meters per second square and the mass of bowman is 50 kg. And what is my target variable? My target variable is normal reaction, that is bowman is applying onto this weighing scale. So to further illustrate this, basically when you stand up on any weighing scale, what you do, you try to push this weighing scale. So you are trying to apply the force. So if you consider, let's say this is your weighing scale and you stand up on this weighing scale. So what exactly you are doing? You are trying to push the weighing scale in the downward direction. So you are trying to push this weighing scale in the downward direction. Let's say the amount of this force is N and same force normal reaction is applied by this weighing scale onto you. That is the normal reaction N. And my target is basically to calculate the reading of weighing scale. So what weighing scale will measure? It will simply measure the force or the normal reaction that is applied onto this weighing scale. So basically weighing scale measures the normal reaction and that's why the reading of this weighing scale is normal reaction, and in this case we have to find the normal reaction. But more important point, the bowman is inside the elevator. So the acceleration of elevator or deceleration of elevator is same as the deceleration or acceleration of the bowman. So I can say acceleration or deceleration, in this case magnitude, A value is equals to 2 meters per second square, and this is applicable for elevator and this is also applicable for bowman. Now how will you solve this problem? So you have the elevator and then what you can do is you can draw the free body diagram on this bowman, and then once you have free body diagram you can apply Newton's second law. So first step is to drawing the free body diagram and then you apply Newton's second law and then you write basically equations. So once you have the equation, you can solve this equation and you can get the normal reaction. In this case, you have only one unknown, that is the normal reaction. You require only one equation. So let us first draw this free body diagram and then we can write equations. So if I consider bowman, so this is, I can show this bowman with a point mass. So there is a force that is acting on this bowman in the upward direction, and this force is nothing but normal reaction. With the same amount of force, she is trying to push the ground, or in this case weighing a scale. So the force that is acting in the vertical direction is normal reaction. Her weight is also acting and this will act in the downward direction, and magnitude is mg. Now the tricky part about the acceleration. This elevator is going in the downward direction with decreasing the speed. So this means it has a deceleration in the downward direction. So you will have an acceleration of the same amount in the upward direction with a magnitude of 2 meter per second square. So you can write A is equals to 2 meter per second square in the upward direction. In other words, you can say since this elevator is decelerating in the downward direction, it is basically accelerating in the upward direction, and that is the magnitude is 2 meter per second square. Now I know by free body diagram I can apply or I can write equation of motion. So the total forces in the y direction is equals to mass into acceleration in the y direction. So what are the forces that is acting in the y direction? Normal reaction plus mg, but mg is acting in the downward direction. That's why we have to put a minus sign. Is equals to mass into acceleration. In this case, acceleration is in the upward direction, that is A. So from here I can calculate normal reaction. So this is nothing but mg plus A. So this is the normal reaction that Bowman will experience, and the same amount of force will be applied to this weighing scale. So let us calculate this normal reaction. Mass of Bowman is given, that is 50 kg, and G value is 9.8 meter per second square, and in this case acceleration is 2 meter per second square. So if you calculate all this will come 590 Newton. Now you can also simply calculate weight of this Bowman. So weight will be nothing but mg. M is 50 kg and G is 9.8 meter per second square. So this will come 490 Newton. Now see, her actual weight is 490 Newton, but this weighing scale or this bathroom scale is showing a reading of 590 Newton. So 100 Newton extra. So this is not her actual weight, the apparent weight, and that's why this is called apparent weight inside this elevator. So she is experiencing extra weight. This is because since she is going in the downward direction and the acceleration is in the upward direction, basically elevator is trying to push her. So she will experience 100 Newton of extra force. So when that elevator is going in the downward direction, this is coming to rest. By decreasing its speed, to decrease the speed, elevator is applying a force in the upward direction. In other words, we can say to have an acceleration in the upward direction, this lift is applying a force in the upward direction, and that's why her apparent weight has increased by 100 Newton. So in this case, apparent weight is 590 Newton, but the actual weight is only 490 Newton, and the increase in weight is due to the fact that this lift is coming to the rest or decelerating, or in other words, it is accelerating in the upward direction. To accelerate in the upward direction, lift has to apply a force, and this force is equals to 100 Newton on this Bowman, and that's why the apparent weight is larger than the actual weight. So I can summarize this fact. In fact, all of you have experienced this. For example, if you are going inside an elevator, so let's say this is a multi-story building, this is the top floor and this is the bottom floor. So if you are coming from top floor to the bottom floor, initially this elevator will start from zero velocity and it will accelerate, its speed increases. At that time you feel light, that is your actual weight is greater than the apparent weight. This means you feel lighter. So in this case you feel lighter. In this case velocity is in the downward direction and acceleration basically is also in the downward direction. Now when this is coming to the ground floor or bottom floor, this elevator has to decelerate so that it can finally come into the rest. So this is decelerating. So this is decelerating. In this case velocity is still in the downward direction, but acceleration is in the upward direction because this is decelerating. So you feel yourself heavy. So in this case you feel more weight. So you feel yourself heavy in this case. So this is the idea. How do you calculate the apparent weight? The only important point you have to consider the direction of acceleration, and everything is simple. If you are going downward direction and the speed is decreasing, this means decelerating. This means your acceleration is in the upward direction. So you have to show the acceleration in the free body diagram in the upward direction. But if you are going in the downward direction and you are increasing your speed, this means you are accelerating yourself in the downward direction. In that case, you will have a acceleration that is positive. Basically, we will have acceleration in the downward direction. So I hope you like this video, and if you like, then please share with your friends and like and subscribe to this video. I will see you in the next video. Thank you. Hello friends. In this video, we will continue our examples on Newton's second law, and we will see how to calculate apparent weight in case of an accelerating elevator. So what is apparent weight? So apparent weight is a weight that you feel when you are inside an elevator. Let us suppose we have this elevator, and when this just starts its motion from zero velocity and it starts going in the upward direction, and you are inside this elevator, you will feel an extra weight. So this weight that is felt by you is basically apparent weight. You can measure this weight. What you can do is you can put a balance or bathroom scale inside your legs, and you just stand up on that balance. And whatever the reading of that balance will be, that is your apparent weight. Basically, in that case, what happens? You have this balance and you are trying to push this balance in the downward direction. And the same way, this balance also try to push you in the upward direction. So this normal reaction, that is the reading of this balance, is the apparent weight. So now in this video, we will basically derive a general expression for calculating the apparent weight. In this case, there are four possibilities. One possibility, you have just started and going up, and you have just reached at the top, and this elevator is coming to rest. And then in next case, if you are coming in the downward direction, and then finally you are coming to the ground floor. So we will discuss four cases. So let us discuss these four cases, and we will basically derive an expression for apparent weight in all these four cases. So these four cases are, in the first case, let us say elevator is going down. So this elevator is going down. So this has just started from the top floor. So on the top floor, it was in the zero velocity and it has started to going down. So what will happen? It will try to increase its acceleration. So velocity is in the downward direction, and in this case acceleration is also in the downward direction. Now let us suppose that this has reached to the ground floor, and once it has reached to the ground floor, that is case number 2. In this case, this has just reaching to the ground floor, so velocity is just still in the downward direction. But what about acceleration? So this lift has to come to rest finally. So this has to decelerate. Basically, it has to decrease its speed. So it will experience a deceleration. In other words, it will have acceleration in the upward direction. So velocity is in the downward direction and acceleration is in the upward direction. So this is your case number 1, this is your case number 2, and this is your case number 3, when the elevator has just started from ground floor and it's want to go to the top floor. So what will happen? Velocity now is in the upward direction. What about acceleration? So this just started as zero velocity. It has to accelerate. It has to increase its speed in the upward direction. So this way we can say acceleration is in the upward direction. Now final situation, this has just reached to the top floor. So what will the velocity direction? Again, velocity is in the upward direction because this lift is going in the upward direction. But it has to come to rest. This means it has to decrease its speed. So it has to have a deceleration. So this means velocity is in the upward direction, but the acceleration in this case will be in the downward direction. So this is acceleration. Now there are 4 cases. We want to calculate basically apparent weight for all these 4 cases, and the idea is very simple. We have to draw the free body diagram and then we have to apply Newton's second law. So let us discuss all these 4 cases. First we will draw the free body diagram and then we will calculate the normal reaction, and normal reaction is nothing but the weight, that the force that this moment is applying over this balance, and similarly this balance is also applying a normal reaction to this moment. So let us draw free body diagram of this moment. So what are the forces that is acting on the moment? One force that is acting is its weight, that is mg, and the balance is applying a normal reaction in the upward direction, and this is normal reaction. Now in this problem, let's say if I assume that the positive direction is the upward direction, that is my sign convention. So this is the sign convention, that is the upward direction is the positive direction. So let us write Newton's second law. So in the force in the upward direction is normal, that's why it's positive. Mg is in the downward direction, so we have to write its negative sign, that is minus mg, that is total forces in the y direction is equals to n minus mg. And now I have to equate this. Force is equals to mass into acceleration. So mass of this moment is m, and acceleration is in the downward direction, that is in this direction, and I have assumed that positive direction is the upward direction. So in this case acceleration is again negative. So from here I can calculate normal reaction, that is nothing but mg minus ma, or I can write this is nothing but m times g minus a. So this is the normal reaction in this case, and this is the apparent weight that this moment is going to experience. So you see, apparent weight is less than mg. So you are basically subtracting something from mg minus ma. So apparent weight normal reaction is less than mg. So she will feel little bit lighter in this case. So when the lift is coming down and this is accelerating in the downward direction, something like from the top floor, you will feel little bit of less weight of yourself. This is the apparent weight less in this case. Now let us consider situation 2. So in this case again we have to draw free body diagram for this moment. So let us denote this moment using a point. What are the forces that is acting? Mg is acting in the downward direction and normal reaction is acting in the upward direction in this case again. So this normal reaction is acting in the upward direction and acceleration is in the upward direction. So now I can write equation of motion, that is n, that is positive, mg is negative because this is in the downward direction, is equals to mass times acceleration. Acceleration is upward and we have assumed that the upward direction is the positive direction, that is my sign convention for this problem. So from here I can write n is equals to mg plus ma, or I can write this is nothing but n is equals to m times z plus a. So you see, in this case the moment is going to experience more force, or she will experience more weight. So apparent weight in this case is more than the actual weight. So for downward journey, when you just started from the top floor, you will feel lighter. But when this is coming to the ground floor, you will feel heavier. So this is for downward journey. That is, you are coming from top floor to the ground floor. So when this just starts its motion, you will feel heavy. You will feel lighter. And when this is coming to the rest, you will feel heavy. Basically, you can experience this whenever you are in the lift or you are in the elevator next time. Now let us consider situation 3. What are the forces acting? Once again, normal reaction, and mg in the downward direction, and normal reaction is in the upward direction, and acceleration is in the upward direction. So this situation is same as this situation. So you can write Newton's second law, that is n minus mg is equals to ma. So in this case again n is equals to mg plus a. So you will feel little bit heavy in this case again, because this is accelerating in the upward direction. Basically what happens in this case, lift is trying to push you, and that's why you feel heavy. Lift is trying to push you, and you also have to remember the acceleration of lift and acceleration of this moment is same, because both are having the same acceleration. So this is a single system. This moment is not flying in the upward direction or going in the downward direction. So we can say acceleration of elevator and acceleration of moment is same, and that is a in this case. So you see, when this is in the ground floor, either it's just coming or it's just going from the ground floor. In both cases you will feel heavy, and the apparent weight will be n is equals to mg plus a or mg plus ma. Now this situation, that is situation number 4, is same as situation number 1. Now you can write Newton's second law in this case once again. Let us first draw free body diagram. mg is in the downward direction, normal reaction is in the upward direction, and acceleration in the downward direction. So we can write n minus mg is equals to mass time acceleration, and acceleration is in the downward direction. That's why you have to put a minus a, because I assume that the positive direction is the upward direction. So n is equals to mg minus a. So this is the apparent weight that the movement will experience when just reaching to the top floor. So you see, in both cases C will experience basically lighter, and in these two cases C will experience a higher weight or higher weight than the actual weight. So apparent weight is the higher. So we can summarize all this. So when you are going onto the top floor, either you are going onto the top floor or you are coming from the top floor, you are going to feel lighter. So you are going to feel lighter in this case. Now when you are going to come onto the bottom floor or the ground floor, in that case either you are going up from the ground floor or you are coming to the ground floor, you are going to, your apparent weight will be more than the actual weight, and you will feel yourself heavy. And this is because in this case basically lift floor is trying to push you, and that's why you feel yourself heavy. So this is bottom floor. So in this video you have seen how to calculate apparent weight in case you are inside an elevator, and I will say whenever you are in the elevator next time, try to experience this. So when you are coming from the top floor, you will feel yourself lighter, and when you are coming to the ground floor, you will feel heavy. And the same thing when you are going to the upside, that is from first floor to the 10th floor. Let's say this is a 10th story building. On the first floor you will feel heavy, on the 10th floor you will feel yourself lighter. Remember, only acceleration happens at the ground floor and at the top floor. So this elevator lifts, this elevator basically accelerates only at the ground floor or at the top floor. It can accelerate or it can decelerate depending upon in which direction you are going. But in the middle, elevator moves with a constant velocity. So remember, that's why you don't feel apparent weight in the middle of the journey. You don't feel apparent weight. You only feel apparent weight, change in the weight at either it is coming to the rest or it has just started to the motion. I hope you enjoyed this video, and if you enjoy, please share with your friends and like and subscribe. You can also comment in the section, and I will see you in the next video. Thank you. Hello friends, in the last videos we have seen how to apply Newton's law on a horizontal surface. Now in this video we will see how to apply Newton's second law on a inclined surface. So the objective of this session is to calculate the acceleration down a hill. So let us discuss this problem. So this problem says a toboggan loaded with students, total weight W, slides down a snow-covered slope. So this is a snow-covered slope and this is the toboggan, this is filled with the student. And this toboggan is sliding down this incline. Now this is a snow-covered slope, so we can assume the friction on this surface is very small. In other words, we can make an assumption that the friction coefficient of this inclined plane is 0. Question further says, the hill slopes at a constant angle alpha. So the angle of inclination of this hill is given and this is alpha. And the toboggan is so well waxed that there is virtually no friction. So there is some waxing also on this toboggan. So one thing is this is a snow surface and this is waxed. So we can assume there is no friction that is acting between this toboggan and this inclined surface. That is a smooth sliding. Now question says, what is its acceleration? So we have to calculate acceleration of this toboggan. So let us try to solve this problem. So first, what are the things that is given? So we have been given weight of toboggan, that is W, and we have been given angle of inclination alpha. So what is our target variable? So target variable in this case, that is unknown, that we have to find, is the acceleration of the toboggan, A value. Now how will you solve this problem? So if you remember, we can use Newton's second law, that is force is equals to mass into acceleration, to find acceleration. So to apply Newton's second law, we have to first draw the free body diagram. So flow chart for solving this problem will be, first draw the free body diagram, and once you have the free body diagram, you can apply Newton's second law. That is, you can write equation. So Newton's second law. So using Newton's second law, you can write equation, and then finally you have to solve this equation and get the unknown, and in this case target variable or unknown is acceleration of this toboggan. So let us try to draw the free body diagram first. So this is the inclined plane. Basically, if you see, initially you have inclined plane something like this, and I am showing something like this. That is, I have kept left thing on the right side. It doesn't matter because finally the shape is same. Now this toboggan, I can show this as a point mass is here. So what are the forces that is acting? One force is the weight of toboggan that is acting in the downward direction. Another force, that this incline is trying to push this toboggan in the perpendicular direction. Let's call this force as normal reaction N. Any other force? Since this surface is frictionless, that is mu is equals to 0, there is no friction along the incline. So to write Newton's second law, we have to choose an axis. So if you remember, in the previous chapter also we said, if we have an inclined plane, we take the axis along the inclined plane, that is my x-axis, and perpendicular to the inclined plane. In this case, this is my y-axis. So this is the axis. Now we have to take the component of the forces along the x and y-axis. So normal reaction is already along the y-axis, but the weight, this is not along the x-axis and the y-axis. So we have to take the component of weight along the x-axis and y-axis. and this angle is given, this angle is alpha, so this angle will also be equal to alpha. So if I take component of W in this direction, this will be W cos alpha. Similarly, in this direction you will have another component, that is W sin alpha. Now I can remove this force because I have already considered its factor or its effect, and that's why we have made a bigly sign, so that we have to remember ourselves that this force will not come into the picture when we are going to write the equation of motion. Now let us write equation of motion. So we can first write equation of motion along the x-axis, that is x direction. So what are the forces that is acting along the x direction? We have W sin alpha that is acting negative x direction, so we can write minus W sin alpha. So force is equals to mass into acceleration. Mass is m and acceleration is ax. Basically we can calculate mass, that is nothing but weight divided by gravity. So weight is given in this problem, so mass is equals to weight divided by z. So let us plug this, so we can write minus W sin alpha is equals to mass times acceleration, and mass we know that is nothing but W by z, so we can plug here and ax. So from here I can get, so this W cancels, so I can write ax is equals to minus g sin alpha. So this toboggan has a acceleration in this direction, that is the negative x direction, and the magnitude is g sin alpha. So we can say acceleration of toboggan, this is equals to g sin alpha, and this is down the incline, this is not up the incline, so this shows the direction, that is down the incline. So toboggan is T-O-B-O-G-G-A-N. So this is the spelling of toboggan. So this is the acceleration of toboggan. Now you see, for calculation of this acceleration, that is x is equals to g sin alpha, we don't need the second equation. We can write the second equation, that is perpendicular to the x-axis. If you write perpendicular equation, the force is N. Force is equals to mass into acceleration. But there is no acceleration. Any other forces that is acting? So one force is normal reaction and another force is W cos alpha. And that is negative bidirection. So we can write minus W sin alpha, basically W cos alpha. So this is W cos alpha, and along this direction there is no acceleration, so this is equals to mass into acceleration. Acceleration is 0, so from here I can write N is equals to W cos alpha. So second equation gives you how to calculate the normal reaction, that is what is the magnitude of the normal reaction. First equation gives you the acceleration value, second equation gives you the magnitude of normal reaction. Let us see some special cases of Ax. So we calculated Ax is equals to g sin alpha. So this is the acceleration value. Now let us consider some special cases. So this is my incline and this is angle alpha and this is acceleration, that is g sin alpha. Now the first situation we can have, that is alpha is equals to 0 degree. In this case, what will be the acceleration? If you put alpha is equals to 0, sin is equals to sin 0 is equals to 0, so Ax is equals to 0, which makes sense because alpha is equals to 0. In that case, this plane will come below and finally it will become a horizontal plane. So if you have a horizontal plane and this toboggan is kept on a horizontal plane, it will not have any acceleration. So this makes sense, that is in this case Ax is equals to 0. The second special case we can have, that is alpha is equals to 90 degree. So if you plug alpha is equals to 90 degree in this equation, x is equals to g sine 90, and sine 90 degree is nothing but 1. So this is equals to z. So acceleration is equals to z. Now when we will have alpha is equals to 90 degree, this means you have to open up this inclined plane. So finally this will be something like this. So this is your inclined plane, and in this case alpha is equals to 90 degree, and toboggan is somewhere here. So this toboggan is going to basically fall freely. So there will be free fall, and that's why acceleration is g. In this case you will have a free fall, and the acceleration in this case is equals to gravity, and that is equals to z. So I hope you enjoyed this video, and if you enjoyed, please share with your friends and like and subscribe. You can also comment in the section, and I will see you in the next video. Thank you. Hello friends, in the last video we have seen how to apply Newton's second law, and we have seen you can apply Newton's second law on a horizontal surface, you can apply on an inclined surface, and if you have two objects that are connected by a string, you can apply Newton's second law. In continuation to that, in this video we are going to discuss how to apply Newton's second law when you have two bodies with the same acceleration. And this we will illustrate using a problem. So this problem says you push a 1 kg food tray through the cafeteria line with a constant force of 9 Newton. So this is the food tray that you are trying to push. So how much force you are applying, this is given. So you are basically applying a force of 9 Newton on this food tray. The tray pushes a 0.5 kg cartoon of milk. So there is a cartoon of milk. So this tray is trying to push this cartoon that contains milk. The tray and cartoon slides on a horizontal surface so greasy that friction can be neglected. Both objects, that is tray and milk cartoon, are kept on a horizontal surface, and this surface is very smooth, greasy. So we can assume there is no friction. So we can say this is moving on a frictionless surface. That is, we can assume the friction coefficient is 0. Find the acceleration of the tray and the cartoon and horizontal force that the tray exerts on the cartoon. So we have to find acceleration of tray and cartoon, and we have to also find horizontal force that the tray exerts on the cartoon. So this force. So what are the things that is given in this problem? So we have been given mass of tray. So mass of tray is given, and that is 1 kg. We have been given mass of cartoon, that is mc, and this is 0.5 kg. And the force that is applied, that is also given, that is 9 Newton. Then what is my target variable? That is, what is unknown? One unknown is, what is the force by which this tray is trying to push this milk cartoon? So let's say this force is R. So we have to find force R that is applied by the tray on the milk cartoon. From the Newton's third law, we can also say the same amount of force will be applied on the tray by the milk cartoon, and these two forces will be equal, and I am assuming this force is equals to R. So R is unknown. So we have to calculate or determine the value of R. We have to also find acceleration of the tray and cartoon. Now see, the cartoon and this tray both will have same acceleration. Try to see this. If you are trying to push this tray, and this will move with the same amount, this milk cartoon and tray will move with the same amount. If this moves by X amount, this will also move by X amount. So we are assuming that this tray and milk cartoon always remains in contact. This means the amount of distance traveled by the cartoon and amount of distance traveled by the tray is same, and that distance is x. So if distance is x, we can say acceleration of these two are same. So cartoon is moving with acceleration a and tray is also moving with acceleration a. So we have to calculate this acceleration also. Now how will you solve this problem? Basically, to solve this problem there are two methods. In one method, what you can do is you can consider this as a system, that is cartoon and tray is a system, and on this system there is external force F is applied. That is one method. That is method 1, let's call. And in another case, that is the second method, what you can do is you can consider separate bodies. That is, now you will consider this as one body and the tray as another body, and then you can basically draw the free body diagram, and then you can apply Newton's second law separately on these two bodies, and then you can basically calculate the unknown. So there are two methods to solve this problem. One method in which you separately consider each object and write Newton's second law. In another method, what you do is you consider a composite object, that is object containing a system containing both objects. So we will illustrate this example using both method, and both method will result in the same answer. So let us use first method to solve this problem. So in this method, we will separately consider this object, that is cartoon, and then we will separately consider this, that is by foot tray. So let us draw the free body diagram, because if you want to find acceleration, you can use Newton's second law, force is equals to mass into acceleration. But to apply Newton's second law, you must know how to draw free body diagram. So let us draw free body diagram of this cartoon. So what are the forces that is acting on this cartoon? So on this cartoon, there is a weight that is acting in the downward direction. Let's call MC is the mass of cartoon, and then I have to multiply by Z. Normal reaction is also acting in the vertical direction. Now this tray is applying a force, and this magnitude, the force magnitude is R, that we already said earlier. So this is trying to push by a magnitude of force R. So this is the free body diagram of milk cartoon, and the milk cartoon is moving in this direction with a acceleration A. Similarly, I can draw free body diagram of foot tray. So what are the forces that is acting on the foot tray? So on the foot tray, you are applying a force F. So one force is that is applied by you, this force is F. In vertical direction, weight is acting, that is mass of tray times Z, and you will have a normal reaction. Let's call this as a normal reaction is N2, and this normal reaction as N1, because these two normal reaction will not be same, these two normal reaction will be different. Any other force that is missing in this free body diagram? Yes, there is one more force that is missing, because this milk cartoon is trying to push this in this direction with the same amount of R, because we know from Newton's third law, if tray is applying a force on milk cartoon, then milk cartoon will also apply a force of same magnitude on the foot tray in the opposite direction. So we have to include this force. So this force is R, that is acting in this direction, and once again acceleration of foot tray is again in this direction, and the magnitude of these two acceleration are same. Now see, in this problem, both object, that is milk cartoon and foot tray, are having same acceleration, and both are having same direction as well as same magnitude. So acceleration is same in terms of magnitude as well as direction. You will see in next videos that sometime you can have magnitude is same but the direction is not same. For example, you have a object, two object that is moving on a pulley. So that we will discuss in the next video. So now to apply Newton's second law, we have to choose a coordinate system. So let us choose a coordinate system, that is, if you are in this direction, that is my x direction, and this is my y direction. So this is the coordinate system that I am choosing, because acceleration are in this direction, and that's why this direction I am assuming this is a positive direction. So let us write Newton's second law for cartoon and tray. So let us first write for cartoon. So what are the forces that is acting on the cartoon? So only one force is acting in this direction, that is R. So force is equals to mass times acceleration. So mass of cartoon is mc and acceleration is a. So let us call this is equation 1. You can also write vertical direction equation, that is bidirection equation. So in the bidirection, total force is N1 minus mcg, because mcg is in the downward direction and this object is not accelerating in the vertical direction. So force into acceleration is equals to 0, because acceleration is 0 in this case. So this is for cartoon. Now let us write Newton's second law for tray. So in this direction, one force is acting, that is F. And in this direction, that is R, that is basically negative. So total forces is equals to mass into acceleration, and mass of this tray is mt and acceleration is a. That is because both objects are having same acceleration. So this is Newton's second law for this object in the horizontal direction. Let us call this equation 3. We can also write vertical direction equation, but that will not be so useful, but let us write. So N2 is the vertical force minus mtg, that is in the downward direction, that's why we have a negative sign. So force is equals to mass into acceleration, and acceleration in this case is 0, so we have to equate this with the 0. So there are 4 equations, and basically we have 4 unknown R, N1, N2 and acceleration. So unknowns are R, N1, N2 and acceleration. So in this problem we have to only find R and A. So that is, we can use equation 1 and equation 3. So let us plug the value of R from equation 1 into equation 3. So what we can do is, from equation 1 to equation, so this is from equation 1 to equation 3. So we are plugging the value of R. So I can write F minus R. R is nothing but mc into A, that is coming from equation 1, and this is equals to mt into A. So from here I can write F is equals to mc plus mt into A. So this is the force. So from here I can get acceleration, and that is nothing but A is equals to F divided by mc plus mt. So this gives me the value of acceleration. So we can calculate this value because I know this. I know the numerical value, so I can calculate this acceleration. So A is equals to, force is given, that is 9 Newton, and the mass of cartoon is, that is 0.5 kg, and mass of tray is 1 kg. So if you calculate this, this will come 6 meter per second square. Now once you know acceleration, you can use equation 1 to calculate force on cartoon, that is R. So we can use equation 1 to calculate force on cartoon. So let us calculate force on cartoon. So we have R is equals to mc times A, and mass of cartoon is 0.5 kg, and acceleration is 6 meter per second square. So this will come 3 Newton. So force on cartoon is equals to 3 Newton. So we have basically solved for A and F, that is the reaction force R that is applied by the tray on the milk cartoon. So we calculated the two unknown by considering the two objects separately. Another method that I said earlier, that you can consider these two objects as the same body, that inside the system these two objects are there, and then you can still apply the Newton's second law. So in this case, this is my system. So let us draw the free body diagram. So on this system, what is the forces that is acting? Only one force, that is F, that is acting in the horizontal direction, and this system is moving with acceleration A, because you see this one and this one both are having same acceleration in terms of magnitude and in terms of direction. So we can say that this is moving with acceleration A. So if I consider only the x direction motion, you can draw the free body diagram by showing the bidirection also. So this is my tray plus cartoon system. The force is acting in this direction. This is F, and then you have this is acting in the downward direction. That is basically mc plus mt into z, and then you have a normal reaction that is different than the previous normal reaction N1 and N2. Now you apply the Newton's second law in this direction, that is x direction, and this is positive direction. So we can write force that is acting is equals to F, and 2 is equals to mass into acceleration. So mass of system is basically equals to mc plus mt, and this is equals to into acceleration. So I can write acceleration is equals to F divided by mc plus mt. So this is the same magnitude that we calculated in the previous part. So once you have acceleration, you can basically calculate reaction force that is applied by this onto this cartoon, by the tray on the cartoon. So how will you calculate that force? Basically now you know the acceleration of this cartoon is this much. So once you know this, you can calculate force. So force is equals to mass times acceleration. So now we can use for cartoon, so we can use for milk cartoon Newton's second law, and I can write force is equals to mass into acceleration, and since this is accelerating in the x direction, force is also in the x direction. So from here I can write Fx is equals to mass is given, and mass of this is cartoon mc, and acceleration is nothing but F divided by mc plus mt. So in the x direction, force is equals to mc F divided by mc plus mt. So you can plug these values and you can calculate basically F. So if you will calculate, this will again come 3 Newton, and this acceleration will again come is equals to 6 meter per second square. So you see, basically I can solve the same problem by two methods. In the first method, what we are doing is we are considering different component of a system and we are drawing free body diagrams separately. And then we are applying Newton's second law separately. But in the second method, we are basically considering a system. And then in that system, both objects are moving with the same acceleration in terms of magnitude and in terms of direction. That's why I can easily apply Newton's second law and I can calculate forces, internal forces as well as acceleration of the system. Now when I should use method 1 or when I should use method 2? That is important point. Generally, it is always advisable that you should use method 1. That is, you should treat each object separately. If you want to use second method, that is, if you want to consider the composite system, in that case, the assumption is your all objects should have same acceleration. If acceleration of objects are different in terms of magnitude or in terms of direction or in terms of both, in that case, the second method, that is method of composite, will not work. I hope you enjoyed this video, and if you like, then please share with your friends and comment below in the section. So I will see you in the next video. Thank you. Hello friends. In the last video we have seen how to apply Newton's second law to a system that contains two objects and these two objects are having same acceleration. That is, they are having same magnitude of acceleration and they are having same direction of acceleration. So in such cases, basically you can consider a composite system, overall system, and you can apply Newton's second law and you can solve for the unknowns. But now in this video we will discuss a system that contains two objects, but these two objects are not having same acceleration. That is, they can have different direction or they can have different magnitude, or they can have both direction as well as magnitude is different. For this problem, we will consider a case when the magnitude of two objects is same, but the direction of acceleration of these two objects are different. So the objective of this session is to learn about how to solve two bodies with the same magnitude of acceleration using Newton's second law. And this we will illustrate using a problem. So this problem says, the figure shows an air track glider with a mass m1 moving on a level frictionless air track in the physics lab. So we have a glider of mass m1. So this is the glider. And this glider is moving on this air track. So this is the air track. And this air track is kept in the physics lab. And this air track is basically friction. So this part is frictionless. So there is no friction between glider and air track. The glider is connected to a lab weight with mass m2 by a light, flexible, non-stretching string that passes over a stationary frictionless pulley. So this glider is connected to mass m2. This is kept in the lab. So this weight is kept in the lab. So we are simply attaching this mass with this glider using a string, and the property of this string is given, that is, this is a light string, flexible string and non-stretching string, and this passes over a frictionless pulley. So this pulley is also frictionless. Now we have to find the acceleration of each body and the tension in the string. So we have to find acceleration of each object and the tension in the string. So in this case, the target variable is, so what is the target variable? Acceleration of each object and the tension in the string. And what are the things that is given? So we have been given mass m1 and then we have been given mass m2. So masses of each objects are given, that is m1 and m2. So m1 is given and m2 is given. And we have been also given properties of a string, that is a light string. So the string is massless. So we can assume the tension throughout the string, that is this point, this point, this point, or this point, or this point, it's same. And we call this tension as T. And this is also given, this is a non-stretching string. So a string is not going to stretch. It's not going to elongate. This means if this point of a string moves by an amount x in this direction, this point of a string will also move amount x in this direction. In fact, all the points will move by the same amount. So we can say acceleration of mass m2 is acceleration of mass m1. So both are having same acceleration, and we will assume that this acceleration is a, then this acceleration is also equals to a. So both are having the same acceleration, and this is frictionless, so there is no friction here. So we can assume this is equals to mu is equals to 0. No friction here, mu is equals to 0. Now how we will solve this problem? So you see, in this case, this object and this object are not having same acceleration, because one is moving along the y direction, another is moving along the x direction. So they are having same magnitude, but direction is different, and that's why we cannot consider a composite system. We have to consider in this case two separate objects, that is, one object is glider, another object is weight m2, and that is mass m2, and we have to draw the free body diagram, and then we can solve the problem. So let us first draw the free body diagram for glider. So let us draw the free body diagram for glider. So we can show this glider using a point, and the beat is acting, and this will be acting in the downward direction, and the magnitude is m1g. And on this glider, a normal reaction will also act. So this is the normal reaction that is acting in the vertical direction. And the string is trying to pull this glider in this direction. So a string will apply a tension, and the magnitude of this tension is T. And this glider is moving in this direction with acceleration A. Now let us write or draw free body diagram for mass m2. So this is mass m2. So once again I will show this using a point, and the weight is acting in the downward direction, and this is m2g, and tension is acting in the upward direction, and this is tension T, and this is moving in the downward direction with acceleration A. So we can show the acceleration A somewhere here. So now once I have the free body diagram ready, so this is the free body diagram for glider. So this is the free body diagram for the glider, and this is the free body diagram for mass m2. Now I can use Newton's second law, but before using Newton's second law, I have to set the axis, that is sign convention. Now in this problem we will use direction of acceleration is a positive direction. This means this mass is moving in this direction. I will consider this is a positive direction. So this is my bi-direction, and this is my positive bi-axis. So this is positive bi-axis, and this mass is moving in this direction, that is this direction. So we'll consider this direction as a positive x direction. So this is my sign convention for this problem. So now using this sign convention or using this axis, we can write equation of motion. So let's first write equation of motion for glider, and we can write equation of motion for x direction first, and then we can write for y direction. So in the x direction for glider, we have only one force, and that is tension. So we can write tension is equals to, that is force is equals to mass into acceleration. Mass is m1 and acceleration is a. Because this is frictionless, there is no force or friction force is acting along the x direction. So this is my equation number 1. For glider in the x direction, we can also write equation for the glider in the y direction. So in the y direction, there is no acceleration, and the force is acting. m1g is in the downward direction, and my downward direction is positive, so I can write m1g, and normal reaction is in the upward direction, and upward direction is negative. So force is equals to mass into acceleration, and acceleration is 0 in the y direction for this object. So I can simply equate equals to 0, and then this is my second equation. Now similarly I can write equation for mass m2. So let us write equation for mass m2. So you see this object is moving in the downward direction with acceleration a. So we can write m2g is the force that is in the downward direction. My downward direction is positive, and tension is acting in the upward direction. So tension becomes negative. So this is equals to force on the bi-direction on mass m2. Force is equals to mass into acceleration. Mass is m2 and acceleration is a. This is my equation number 3. So this is for bi-direction. Now in this case for mass m2, there is no point of writing an equation in the x direction, because in the x direction there is no force and there is no acceleration. This means this is simply 0 is equals to 0. Now I can solve these two equations. So what I can do is I can plug the value of t from 1 in equation 3. So from 1 in equation 3. So this is from equation 1 in equation 3. So I am simply writing 1 and 3, that denotes equation 1 and equation 3. So from 1 I can write t is equals to m1a. So equation 3 is nothing but m2z minus t is nothing but m1a, and this is equals to m2a, and this gives you m2z is equals to, I'm taking this right hand side, so I will have m1 plus m2a. Now if you solve this, you can get basically a is equals to m2z, and this divided by m1 plus m2. So now I can write this acceleration is nothing but m2 divided by m1 plus m2, and this multiplied by z. This also makes sense because this is a dimensionless quantity and acceleration will have a dimension of z. So this is mass by mass, so there is no dimension in this case. So this is the acceleration of both object, the mass m, and this glider also will have the same acceleration. Once I know the acceleration, we can also calculate tension in the string, and tension is nothing but m1a as I showed earlier. So from here I can write t is equals to m1, and acceleration we just calculated, that is m2z divided by m1 plus m2. So this becomes m1 m2 divided by m1 plus m2, and this multiplied by z. So tension is nothing but m1 m2 divided by m1 plus m2, and this multiplied by z. Now see the dimension of tension. So this is dimension of force, because this will have a dimension of mass, because one mass will cancel out, so this will have a dimension of mass, and this is a dimension of acceleration. So you can say the tension will have a something like in Newton. Now we can consider two special cases. So a special case, the first case we can consider what will happen if m1 is equals to 0. This means there is no glider, or glider has a 0 mass. Now if you see this equation, we can calculate acceleration by simply putting m1 is equals to 0. So this m1 is equals to 0, so this becomes simply a is equals to m2 divided by 0 plus m2, and this multiplied by z. So this gives you a is equals to z, and that basically makes sense. If there is no mass, this is 0 mass, there is no mass, this means this mass m2 will fall freely. So there is basically gravity. The acceleration of mass m2 will be z, because this will fall under the gravity. Now the second special case, that is about tension. So when you will have tension is equals to 0, so either mass m1 can be 0 or mass m2 can be 0. In that case tension will be 0. So either mass m1 is 0 or mass m2 is equals to 0. In both cases you will have 0 tension, and that makes sense. This means if there is no object here, you will have no tension in this string, because this string is simply hanging from the pulley. Same way, if you have in this case there is no mass m1, in that case again, so there is no mass m1 in this case. So if there is no mass m1, then this is simply freely falling, and this string is slacked. So this means there is no tension in this case. So in this video we have seen how you can basically analyze a system that contains two objects, and these two objects are having same acceleration, but in magnitude wise same, but the direction wise they are having different the different acceleration direction. And in those cases you cannot analyze this system by simply considering a composite system, but you can analyze this system by considering two objects separately and drawing the free body diagram. In fact, there is a method by which you can draw or you can analyze this system by considering a composite system. But that I will not consider in this session. Somewhere else I will consider that. In that case, what you have to consider is, you have to consider axis something like this. You have to consider a curved axis, something like this. So you have to consider a curved axis, and then you have to write equation of motion along this curved axis, and that is basically one line solution, and you can get the acceleration of this object. So I hope you like this video, and if you like, please share with your friends and comment in the section below, and I will see you in the next video. Thank you. Hello friends, in this video we will see how to use Newton's first law to calculate the frictional forces. So the objective of this session is to calculate the friction force in a horizontal motion. So we will calculate coefficient of a static friction and coefficient of kinetic friction when an object is moving on a horizontal plane. So let us discuss this problem. So problem says you want to move a 500 Newton crate across a level floor. So this is the crate that is given, and the weight of this crate is given. Basically this is 500 Newton, and this is the level floor on which you want to move this crate. To start the crate moving, you have to pull with a force of 200 Newton horizontal force. So if you want to pull this in the horizontal direction, you have to apply a force of 230 Newton. Once the crate breaks loose and start to move, you can keep it moving at a constant velocity with only 200 Newton. So this means you can apply relatively a smaller amount of force to keep this moving with a constant velocity. What are the coefficient of a static and kinetic friction? So we have to calculate coefficient of kinetic friction and coefficient of a static friction. So let us do this problem. So what are the things that is given? So we have been given weight of crate, that is 500 Newton, and we have been given the force. There are two forces. In one situation it just loses its brake. In that case force is equals to 230 Newton. Let's call this as F1. And when this is moving with a constant velocity, force required is 200 Newton. So these two forces are given. And what is my target variable? So target variable that is unknown in this case, that is coefficient of a static friction and coefficient of kinetic friction, that is mu s and mu k. Now how will you solve this problem? You see, there are two situations. In one situation this is not moving. That case crate is in equilibrium. So we can apply Newton's first law. In the second situation it is moving with a constant velocity. Since this is moving with a constant velocity, this is still in equilibrium. So we can apply Newton's first law in both cases. So we will consider Newton's first law, and we will draw the free body diagram, and then we will write the equation, and then we will calculate the coefficient of frictions. So what is the idea? What is the flow chart to solve this problem? So we have to basically first draw the free body diagram. And once I have the free body diagram, I can apply Newton's first law. So Newton's first law, we can apply Newton's first law. And once we have written Newton's first law, we can solve for unknown. That is the flow chart for solving this problem. So solve for unknown. So in this case, unknown is mu s and mu n. So let us try to solve this problem. We will consider two cases, that is case 1, and in this case this is not moving, this is in the rest, so crate is in the rest. So what are the forces that is acting on the crate? So if you consider crate as a point mass, one force is acting that is in the downward direction, that is the weight of the crate, and the floor is applying a horizontal force, so basically vertical force, and that is the normal reaction. Now we are applying, or the person is applying a force in the horizontal direction, and magnitude of this force is F1, and we said earlier this is nothing but 230 Newton. Now this floor on which this crate is kept, so if you try to pull in this direction, the crate will not move because there is a friction force that is acting between surface, that is ground, and between the crate, and this force try to oppose the motion of the crate. So this will act in this direction. So the friction force always try to oppose the motion. So crate tries to move in this direction, so this force will be in this direction. So we can say in this case friction force will act in this direction. Let us call this friction force as F1. What will the magnitude of this force? Magnitude will be mu s times n. Why mu s? Because at this point of time this crate is not moving, so we will use coefficient of a static friction. So now we can write equations, that is Newton's first law we can apply. So let us apply in the x direction and the y direction. So we'll consider this direction is my x direction and this direction is my y direction. So this is the sign convention for this problem. So this is the positive x direction and this is the positive y direction. So now if I consider summation of all the forces in the x direction, this has to be equals to 0 because this crate is in equilibrium. So forces has to be equals to 0, that is if you sum all the forces. So what are the forces acting in the horizontal direction, the x direction? One force is F1, that is this force. Another force, that is friction, that is acting in the opposite direction. That's why we have taken a negative sign, and this is equals to 0 because when the two forces are acting in this case, F1 minus a small f1. Now the friction force we can also write mu s times n in this case. So this is negative sign and this is equals to 0. So this is my equation 1. Now we can also write bidirection equilibrium, that is summation of Fy is equals to 0. So in the y direction we have normal reaction and weight is acting in the downward direction, that's why negative sign, and this is equals to 0. So this gives you normal reaction is equals to weight of the crate. So this is my equation 2. So from equation 1 and 2 I can calculate mu s. So let us plug the value of n in equation 1. So from equation 1 we can write F1 minus mu s, and n is nothing but w, this is equals to 0. So I can further write F1 is equals to mu s times w. So from here I can write mu s is equals to F1 divided by w. And F1 we know that is nothing but 230 Newton, and W is also given in this case. W is 500 Newton. So if you solve this, you will find the mu s value is 0.46. So coefficient of a static friction between the block, the crate and the ground floor is equals to 0.46. So this we calculated by considering equation of equilibrium and considering Newton's first law. Now we will consider the second case. So in the case 2, this is moving with constant velocity. That is, sum of the forces is again 0. So we can still apply Newton's first law. Only difference is, in this case the friction force will be not a static, it will be a kinetic friction because the crate is moving with a constant velocity. So in this case you will have friction force that is kinetic in nature. So let us draw the free body diagram. So this is your object, that is crate, weight is acting in the downward direction. We will have a normal reaction and this force is F2 that we know, that is 200 Newton, and this time friction force, let's call this as F2, and this will be kinetic in nature, so mu k times n. We can write equation of equilibrium. So this is again x direction and this is my y direction. Sum of the forces in the x direction is equals to 0. This means F2 minus a small f2, this is equals to 0. This means f2 minus mu k times n is equals to 0. This is my equation 1. Now I can write sum of the forces in the bidirection is equals to 0. This means normal minus weight is equals to 0. This gives me normal reaction is equals to weight, and this is my second equation. Now if I use the second equation in 1, so from equation 1 I can write f2 minus mu k, and n is nothing but w. This is equals to 0. So from here I can write mu k is equals to nothing but f2 divided by w. And the value of f2 is known, that is 200 Newton, and the weight of the crate is also given, that is 500 Newton. So we can plug this value and we can calculate coefficient of kinetic friction, and this turns out to be 0.4. So now in this case we know that is mu k is equals to 0.4. Basically you can compare the two values, the coefficient of static friction as we calculated earlier, that was 0.46, and coefficient of kinetic friction that we just calculated, that is 0.40. So as expected, you can expect that the coefficient of a static friction should be larger than the coefficient of kinetic friction, and that is the case here. You see the coefficient of a static friction is 0.46, which is greater than the coefficient of kinetic friction, which is basically equals to 0.4. So in this video we seen how do you calculate the coefficient of friction. And there are two types of coefficient of friction. When the object is not moving, the friction forces that is acting on the object, that is static in nature. And when the forces are acting and the object is moving with a constant velocity, in that case you have coefficient of kinetic friction. In both cases, the object remains in equilibrium and you can apply Newton's first law. So we applied Newton's first law and calculated the coefficient of friction for the both cases. I hope you enjoyed this video. If you enjoy, please share with your friends, and I will see you in the next video. Thank you. Hello friends. In the last video we have seen how we can use Newton's first law to calculate the coefficient of static friction and coefficient of kinetic friction. So in that problem we were having a crate and a man is trying to pull this crate with a horizontal force. Now there was two situations. In one case the crate is not moving, and using that you can calculate coefficient of static friction. In another situation the crate is moving with a constant velocity. In that case you can calculate coefficient of kinetic friction. Now in this problem we will illustrate the same thing. Only difference we will have that in this case this force that is applied by the person is not horizontal. So this time the force is inclined to an angle of theta. So the objective of this session is to calculate the force required to pull the crate when the forces are inclined at an angle from the horizontal. So the problem says, suppose you want to move the crate and the weight of crate is given, that is 500 Newton. By pulling upward using a rope at an angle of 30 degrees above the horizontal. So you want to move this crate and the weight of this crate is given, that is 500 Newton, and basically you are applying a force that is at angle of 30 degrees from the horizontal. How hard must you pull to keep it moving with a constant velocity? So question is asking how hard, this means how much force you should apply to this rope so that this crate should move with a constant velocity. This means the crate remains in equilibrium. Since the velocity is constant, acceleration is zero. So this crate is in equilibrium. We can apply Newton's first law. What are the things that is also given? We have been given the coefficient of kinetic friction, that is mu k is equals to 0.4. So what are the things that is given? So in this case you have been given weight of crate, that is 500 Newton, and you have been given coefficient of kinetic friction, that is 0.4, and angle theta is also given, that is 30 degree. And you have to find the force by which this you have to pull. So you have to calculate F. Now this problem and the previous problem, how these two problems are different. In other words, in the previous problem you are having this crate and you were applying a force in this direction, but this time you are applying a force in this direction. How these problems are different? If you see these two problems closely, there is only one difference. In the previous case, normal reaction was this, and in this case, normal reaction is this. But this normal reaction, that is in case of incline, will be relatively smaller compared to this case. So let's call this as N1 and let us call this as N2. So if you compare these two cases, N1 will be greater than N2. So don't worry about this, we will solve this problem, and towards the end we will again come to this point that in this case normal reaction has reduced, and that's why the friction forces has reduced, and that's why you have to apply relatively a smaller amount of force to pull this crate. So how will you solve this problem? So what will be the flow chart for solving this problem? Once again, first I have to draw the free body diagram. So if you have any problem related to Newton's law, the initial thing you have to draw the free body diagram. Once you know the free body diagram, in this case, since the object is in equilibrium, you can use Newton's first law. So let us apply Newton's first law. And once you have written the Newton's first law, you can basically formulate the equation and solve. And that will give you the value of unknown. So what is the target variable in this case? That is unknown in this case is F. So let us first draw the free body diagram. So let us say this is your crate. So what are the forces that is acting on this crate? On the crate, one force that is acting in the downward direction, that is weight of the crate. And the ground is also trying to push this in the upward direction, so there is a normal reaction that is acting in the upward direction. Now since the surface is not smooth, there is a friction, so the surface will try to apply a friction force in the opposite direction of the motion. So this tries to move in this direction. So your crate basically tries to move in this direction with constant velocity. This means friction force will come in this direction, because friction force is always in the opposite direction of the motion. Let's call this magnitude is F, which will be equals to mu k times n. You see, the friction force is kinetic in nature because this object is moving. What are the other forces that is acting? Only one more force, that is the force that you are trying to pull. That force is F. That is the tension inside this rope that you are trying to pull this rope at angle of theta. So this angle is theta. Now let us say I use x-axis in this direction and my y-axis is in this direction. So I have to write Newton's first law in x direction and in y direction. But for that I have to take the component of force F. Other forces are along the x direction or the y direction, but this force is not along the x direction and the y direction. So let us take component. So in this direction you will have F cos theta, and in this direction you will have F sin theta. Now once I have taken the component of this force, I have to basically remove the actual force. But because this time this becomes redundant, I have already taken the effect of F in the two direction, so that you should not use the second time, and that's why we have put a cross mark, sometimes we put a bigly mark, so that we should be careful that this force should not be counted twice. Now let us write Newton's first law. So first we will write in the x direction, that is summation of forces in the x direction is equals to 0, because this is moving with a constant velocity. So what are the forces that is acting in the x direction? One force is F cos theta, and this is also, but this is in the negative direction, that's why we put a minus F, and this is equals to 0, and the f value is known, so we can further write f cos theta minus mu k times n is equals to 0. So this is my equation number 1. We can further write equation 2 by considering equilibrium in the y direction. So what are the forces that is acting? In the y direction we have normal reaction and we have f sin theta. So this plus f sin theta, and the weight is acting in the downward direction, so this is minus w, and this is equals to 0. So from here I can write n is equals to w minus f sin theta. That is my second equation. Now once I have these two equations, I can solve. So let us plug the value of n from equation 2 into equation 1. So from equation 1 we can write f cos theta minus mu k, and n value is known, that is nothing but w minus f sin theta, and this is equals to 0. So from here you can basically calculate this force F. So I can write F cos theta plus mu k. So this and this becomes mu k F sin theta, and this is equals to, this goes this side, so this term becomes mu k times w. So from here I can calculate F is equals to, this is equals to mu k times w divided by cos theta plus mu k sin theta. So if you want to pull this crate at an angle of theta, then in that case the force required is this much. So since I know the numerical values, we can plug all this and we can calculate the value of F. So F is equals to mu k is equals to 0.4, and this is W is 500 Newton and theta is 30 degree in this case. So cos 30 degree and mu k is 0.4 and sin 30 degree. So if you will solve, you will find this turns out to be 188 Newton. You can also calculate normal reaction because that was unknown. In this problem it is not needed and that's why it is not required, but we can calculate normal reaction, that was W minus F sin theta. So you see here you have equation that is normal reaction W minus F sin theta, and we know the value of F, so we can calculate normal reaction. W is basically 500 Newton and this is 188 Newton and this is sin 30 degree. So this will come 406 Newton. So you see the normal reaction is less than weight. What is the weight? That is 500 Newton. So in this case normal reaction is less than the weight. If you pull this with a horizontal, that is you are applying a force in the horizontal direction, in that case normal reaction will be W. You can see if you put theta is equals to 0 degree, if you put theta is equals to 0 degree, you can find this normal reaction is nothing but W, because theta equals to 0, this term becomes 0, so normal reaction is equals to W. So you see if you try to pull with an angle, normal reaction decreases. So if the normal reaction decreases, the friction force also decreases because the friction force is equals to mu k times n. So in other words, you have to apply a smaller force. In this case, you have to apply only 188 Newton. But if you pull with horizontal force, in that case, you have to apply a force of 200 Newton. So if you remember in the previous problem, if you apply a force in the horizontal direction and you want to pull this crate, you have to apply a force of 200 Newton. But this time, this crate, you want to apply a force at inclined angle. In that case, you have to apply only a magnitude of 188 Newton, and this also depends upon theta. So you see, it is always a good idea to pull this crate by applying a force at some angle. This angle can be 30 degree or 40 degree or 60 degree. Basically, you can find a theta for which this force is minimum. You see, what is the expression for the force? So you know the expression for force is mu k times W, and this divided by cos theta plus mu k sine theta. So that was the expression for force. So you can see, if somebody is good in mathematics, he can see this force is a function of theta. Now you want to find theta for which the force applied is minimum. So what I am looking for minimum force, and for that, what is the theta? So I can use calculus, that is, I have to differentiate force in terms of or with respect to theta. So if you basically differentiate force with respect to theta and then plug this is equals to 0, this will give you theta for which the force is minimum. So using this, you can calculate theta, and for that theta the force will be minimum. I think you can do this as a home exercise, and I will see the answer in the comment box. I will request all of you to do this problem as a homework and share your comments in the comment box. So in this video we have seen how good if you apply a force at incline to move a crate. It's always good to pull the crate by some angle. It's not a good idea to pull the crate by horizontal, applying a force in the horizontal direction. I hope you enjoyed this video, and if you enjoy, please share with your friends, and I will see you in the next video. Thank you. Hello friends. In one of the previous videos we have seen how to apply Newton's law on an inclined plane when the friction is absent. Now in this video we will see how to write equation of motion when there is a friction on the inclined surface. And this we will illustrate using a problem. So the objective of this session is to calculate the angle of inclination. In other words, what is this angle alpha for the given problem? So this problem says, let us consider the toboggan as shown in the figure. So this is the toboggan. The incline has coefficient of kinetic friction mu k. So the coefficient of kinetic friction for this incline is given, and this is mu k. The slope has just the right angle to make the toboggan slide with a constant velocity. So this angle is just right so that this toboggan is moving with a constant velocity. This means this remains in equilibrium. So in other words, we can apply Newton's first law. So question says, find this angle in terms of W, that is the weight of the toboggan, and friction coefficient, that is kinetic friction coefficient mu k. So how will you solve this problem? So let us first write the things that is given. So we have been given weight of this toboggan, that is W, coefficient of kinetic friction, that is mu k, and the angle alpha we have to find, that is my target variable alpha. And we have been also given that this toboggan is moving with a constant velocity. So this toboggan is moving with a constant velocity. So how will you solve this problem? So since this is a case of equilibrium, we can apply Newton's first law, and then we can write equations and we can solve these equations. So let us first draw the free body diagram for this toboggan before applying the Newton's law. So this is the toboggan. What are the forces that is acting on this toboggan? So one force that is acting is the weight. So let us show here. So one force acting is the weight. So I can show something like this. So this is my inclined surface and this angle is alpha. It does not matter whether I show like this or I show like this. So this doesn't matter because this is, we are, as long as we are considering all this inclination and angle, so it will not have any difference in the problem. Now what are the other forces? One force, that is normal reaction. So normal reaction will act in this direction. Any other force? So this tried to move in the downward direction. So this is trying to move in the downward direction with a constant velocity. So this surface will try to oppose this motion. To oppose this motion, the surface will apply a friction force that will act in the upward direction. And this friction force is F, and this will be mu k times N. Since this object is moving with a constant velocity, this friction will be kinetic in nature, and that's why we have taken mu k times N, not mu s times N. In this problem also, mu k value is given. So we can use mu k times N to calculate the friction force, and this will act in the upward direction. So magnitude of friction force is mu k times N, and the direction of friction force, this will act in the upward direction. Now whenever you have a problem on incline, you have to basically decompose the forces along the incline, that is my x-axis, and perpendicular to the incline, that is my y-axis. So in this case, I have to decompose my forces along the incline and perpendicular to the incline. So this force is W. So this is W. So I have to take the component. So in this direction, this will be W cos alpha, because this angle is also alpha, and this is W sin alpha. Why this angle is alpha? Because there is a theorem that says angle between line is equals to angle between perpendiculars. So this line and this line, on this line this is the perpendicular, and on this line this is the perpendicular. That's why this angle is alpha. So once I have taken the component, I have to basically remove this force, and we simply put a bigly sign, so that now we are not going to consider this W. Now let us write equation of motion. So first we will write equation of motion in the x direction. Since this is in equilibrium, that is moving with a constant velocity, sum of the forces in the x direction is equals to 0. So what are the forces that is acting in the x direction? One force is mu k times N, that is acting in the upward direction, that is positive direction, and this force that is in the downward direction minus W sin alpha, this is equals to 0. That is sum of the forces. So this is my equation 1. Similarly, we can write sum of the forces in the y direction is equals to 0. So in the y direction we have normal reaction, and this force, that is W cos alpha, that is in the negative bidirection. So minus W cos alpha, this is equals to 0. That is my equation number 2. So you can see these two equations can be used to solve for alpha. So let us, using equation 2, calculate value of N and put into the equation 1. So from equation 1 we can write, mu k, and N that will be coming from this equation, that is nothing but W cos alpha. So mu k times N minus W sin alpha, this is equals to 0. So from here I can calculate alpha. So W cancels out, so we will have mu k is equals to tan alpha. So I can write tan alpha is equals to, so this tan alpha is equals to mu k. One important observation you can say, this angle alpha does not depend upon the weight of the toboggan, that is W. So it does not depend upon the W. So you can have a smaller toboggan or you can have a larger toboggan. In both cases it will move or it will slide with a constant velocity for given friction, and it will not matter at the same angle, it will basically slide. So you can also write alpha is equals to tan inverse mu k or arc tan mu k. So alpha you can also write arc tan mu k. Now you can see if your mu k value is higher, then alpha will also be higher because tan inverse is a increasing function. So if mu k is higher, alpha has to be higher. In other words, I can say if alpha increases, mu k increases, or if mu k increases, alpha increases. In both directions we can see. This basically makes a sense because if you consider this inclined plane, if you increase angle alpha, then in that case, if you want to move this toboggan with constant velocity, you have to increase your mu k. Otherwise, it will accelerate. If mu k value is not that large, in that case, it will start accelerating. So if you want to move with a constant velocity and you are increasing alpha, in that case you have to increase mu k. So if you increase, or if you can make a steep inclined plane or inclined surface, in that case you have to make the surface rough also, so that you can have a constant velocity. So in this video we have seen how we can calculate angle of inclination alpha for a given value of coefficient of friction, that is coefficient of kinetic friction, and these two are related by a function of tan inverse. You can use this problem to solve or to calculate the angle for given mu k value. So I hope you enjoyed this video, and if you enjoyed, please share with your friends and like and subscribe this channel. I will see you in the next video. Thank you. Hello friends, in the last video we have seen how to analyze a object when this object is moving on an inclined plane with constant velocity. Now in this video we will see how to analyze and write equation of motion if the object is moving with an acceleration on the inclined plane. So the objective of this session is to calculate the acceleration down the incline. So we have to calculate the acceleration. What is the magnitude of acceleration if an object is sliding over the inclined plane? And this we will illustrate using a problem. So the problem says, let us consider the toboggan as shown in the figure. So this is the toboggan that we have. The inclined surface has coefficient of kinetic friction mu k. So this surface is not a smooth surface, this is a rough surface, and kinetic friction coefficient is given, and this is mu sub k. Find the acceleration of toboggan in terms of z, alpha, w and mu k. So we have to find with what acceleration this toboggan is moving in the downward direction. And we have been given z, that is gravity, alpha, that is the angle of inclination, and w, that is the weight of the toboggan, and mu k is the coefficient of kinetic friction. So we have been given z, alpha, w and mu k. And what is my target variable? That is, what is my unknown? So we have to find acceleration of the toboggan. So this is the target variable. Now once again, how do you solve this problem? So we have to use Newton's second law because we have to find acceleration. So we have to find forces, and that will come from the free body diagram, and then we can relate force is equals to mass into acceleration. So the first step of solving this problem is to draw the free body diagram. So this is the toboggan. So let us denote this toboggan by a point, and this is my inclined plane, and this angle is given, this angle is alpha, and this toboggan is going in the downward direction. Acceleration is a. Let us assume this direction is my positive x-axis and this is my positive y-axis, that is perpendicular to the inclined plane. So the first force that is acting, that is weight of toboggan, that is W. And there is a normal reaction that will come, and this has value N. what other forces are acting? Since this toboggan has a tendency to go in the downward direction, there will be a friction force on the point of contact or surface of contact between this toboggan and inclined plane. And this friction force will act opposite to the motion. This means towards the up the incline. So this is the friction force that will act in this direction, and the value of this friction will be mu k times normal reaction. That is, this friction force is kinetic in nature. So now to write equation of motion, we have to decompose the forces. So in this direction we have to take the component of W. So this angle is alpha, then this angle will also be alpha. So this is nothing but W cos alpha. And in this direction the component will be W sin alpha. And then I have to delete this because we have taken the consideration, or we have taken into account this W. Now we have to write equation of motion. So let us write equation of motion in the x direction and in the y direction. So in the x direction I can write summation of forces is equals to mass into acceleration. So what are the forces that is acting? One force is W sin alpha. And friction is acting in the opposite direction, that is mu k times n. And this is moving in this direction along the x-axis with acceleration a. So we can basically equate this mass into acceleration. So mass of toboggan is m, and that can be calculated from the weight. Since weight is given, mass is equals to weight divided by z. So this is equation 1 from x direction. Similarly, we can write equation of motion in the y direction. In the y direction we have one force normal reaction, and this W cos alpha is negative because this is acting in the opposite direction. And since there is no acceleration, this is equals to 0. So this is my equation 2. Now from equation 2 I can calculate n value and plug in equation 1. So from equation 1 I can write, so from equation 1 I can write W sin alpha minus mu k, and n is nothing but W cos alpha. So this is W cos alpha. This is equals to, and we said mass is nothing but W divided by z times acceleration. So W cancels out. So we will have acceleration is equals to g comes this side, g times sin alpha minus mu cos alpha. So this is sin alpha minus mu cos alpha. So if an object, or in this case toboggan, is sliding in the downward direction, the magnitude of acceleration will be z times sin alpha minus mu cos alpha. So this is the acceleration by which this toboggan is moving in the downward direction. Now we will consider different cases. Some special cases we can consider for this acceleration. So let us consider some special cases. The first case, when alpha is equals to 90 degree. What will happen in that case? Sin alpha is equals to 1, because alpha is equals to 90 degrees, sin alpha is equals to 1, and cos alpha is equals to 0, because alpha is 90 degree. Then what will the acceleration? In that case, acceleration is simply equals to z. And that makes sense, because what will happen in that case? This angle is alpha. If alpha goes to 90 degree, this means this is your surface and this is your toboggan. So this will fall freely. So when alpha is equals to 90 degree, you will have a free fall acceleration, and that comes from this expression, that is A is equals to z. Now the second special case, when you will have acceleration is equals to 0. This means the toboggan will move with a constant velocity. So for that you should have 0 is equals to sine alpha minus mu cos alpha. So what I am doing, I am simply equating this expression equals to 0. So from here I can say tan alpha is equals to mu, or we can also say alpha is equals to arctan or tan inverse mu. So if you remember, this was the angle that we derived in the previous video when the object was moving or toboggan was moving with a constant velocity. Now third possibility, when the acceleration can be negative. So there is a possibility that acceleration can be negative. So when acceleration can be negative, and acceleration is nothing but z sine alpha minus mu cos alpha. So this is possible for a smaller angles, a smaller alphas. In that case, this term will be large and this term will be a small. So if alpha is a small, because if alpha is a small, cos alpha will be large and mu cos alpha can be greater than sine alpha. In that case, acceleration will be negative. What does this means? Negative acceleration. Negative acceleration means this is the inclined surface and this is your toboggan, and even if you push this toboggan with some velocity, it will go into the downward direction, but the acceleration is negative. This means acceleration is in the upward direction. This toboggan will eventually come to the rest. So we can say for sine alpha is less than mu cos alpha, we will have negative acceleration, and in those cases, even though we push the toboggan in the downward direction, it will eventually come to the rest because of this negative acceleration. And finally, what will happen if the surface is smooth, that is mu k is equals to 0. So if mu k is equals to 0, plug in this expression mu k is equals to 0. So this is my mu k and this is also mu k. All mu are basically kinetic friction of coefficient mu k. So this is mu k. So this is also mu k. So what will happen in that case? You will have acceleration is equals to simply g sine alpha, because this term will be 0. So we will have only one term, that is g sine alpha. So let me check if I have somewhere mu, then I have to replace with mu k. So this is my mu k and this is also mu k. So if mu k is equals to 0, acceleration is simply g sine alpha. That is your simple case that you have inclined plane and there is no friction on the inclined surface. In that case, object will move with a constant acceleration of g sine alpha. So in this video, we have seen how to analyze an object if it is moving or falling over an inclined plane and the surface has some friction coefficient, and we derive a general expression. Now this general expression can be considered and can be thought for different special cases, and these special cases we have basically learned or as a numerical problem in the previous videos. So you see, from the general expression we can derive all the special cases. For example, what happens when this inclined plane becomes vertical, what are the situation when acceleration will be 0, and what are the situation when acceleration will be negative, and what will happen if my surface is smooth. So you see, once I have a general expression, I can consider all the cases, all the special cases, and we can plug the values and we can derive the result for the special cases. I hope you enjoyed the videos, and if you enjoy this, please share with your friends, and I will see you in the next video. Thank you.